Tonight we're exploring how light actually works, from the sunlight entering a room and the colours we see around us, to electromagnetic waves, photons, relativity, and the ancient light arriving from distant galaxies. Just a little favour to ask before we begin. If you have a moment to spare, I'd really appreciate it if you took a look at our ebook over on the Sleepy Scientist website. It takes the ideas from these videos and gives them room on the page, unhurried, laid out with all the space they need to properly settle in the mind. The whole thing is narrated too, so you can read it or simply listen. And at the close of each movement there's a short quiz waiting, a gentle way to see what stayed with you, and to turn the ideas over once more before moving on. The QR code is up on screen, and there's a link in the description to the sleepyscientist.com whenever you're ready. Every reader who takes a look is the reason these videos keep appearing, and to anyone who takes the time to buy it, I don't think you quite understand how much that means. That's the only ask tonight, and thank you sincerely. Now, before we begin, let me know where in the world you're listening from, and what time it is for you. I always enjoy seeing these little check-ins from around the world, as people settle in for the night, or the morning, or somewhere quietly in between. Wherever you're listening from, and whatever time it may be, settle in, get comfortable, and allow yourself to relax. Light is so deeply woven into ordinary life that it can be difficult to notice how mysterious it really is. It arrives through a window in the morning, spreads across a wall, catches on the edge of a glass, reflects from a mirror, and disappears into a shadow. It makes leaves appear green, clouds appear white, and evening skies glow orange. It carries images into cameras, information through fibre optic cables, and warmth from the sun across roughly 150 million kilometres of empty space. Light is familiar enough to be taken for granted, yet unusual enough to have challenged some of the greatest minds in physics. A glowing screen produces light. A red jumper absorbs some wavelengths and reflects others. A polished window redirects part of the light falling upon it, while allowing another part to pass through. A dark shadow forms where light has been blocked or redirected. Every visible scene involves some combination of emission, movement, reflection, refraction, scattering, absorption, and detection. Even the simple act of looking around a room is the final stage of a remarkable physical process. Light must first be produced by a lamp, the sun or another source. It must travel through space, interact with surfaces, and enter the eye. Only then can biological cells and neural circuits transform those physical signals into the experience of brightness, shape, depth, and colour. That distinction matters. Light itself is not the same thing as sight. Light is a physical phenomenon. Vision is a biological and perceptual response to a small range of that phenomenon. Human eyes detect only a narrow band of the electromagnetic spectrum. Visible light usually refers to wavelengths between roughly 400 and 700 nanometers. A nanometer is 1/1000th of a meter, making visible wavelengths far smaller than the thickness of a human hair. Yet this tiny window is only one part of an enormous family of electromagnetic radiation. At longer wavelengths lie infrared radiation, microwaves and radio waves. At shorter wavelengths lie ultraviolet radiation, X-rays and gamma rays. These names describe different ranges of wavelength, frequency, and energy, but they do not represent completely different substances. Radio waves and visible light are expressions of the same underlying electromagnetic phenomenon. The reason they seem so different is largely that they interact with matter in different ways. Human eyes respond to visible wavelengths, but not to radio waves. Water molecules can absorb certain microwave frequencies. Ultraviolet light can drive chemical changes in skin. X-rays can pass through soft tissue more easily than through bone. Gamma rays can carry enough energy to ionize atoms and damage biological molecules. Nature does not divide the electromagnetic spectrum into brightly labelled sections. Those boundaries are human conveniences, rather like drawing lines across a map. The landscape remains continuous even when the regions receive different names. Light can travel through empty space. Unlike sound, it does not require air, water, or another material medium to carry it. Light from the sun crosses the vacuum between the sun and Earth in a little over 8 minutes. Light from the nearest star system beyond the sun takes more than 4 years to arrive. Light from distant galaxies may travel for billions of years before reaching a telescope. This ability makes light one of science's most important messengers. Astronomers cannot collect samples from most stars or visit distant galaxies, but they can study the light those objects release. From that light they can infer temperature, chemical composition, motion, magnetic fields and distance. A faint pattern of wavelengths can reveal what a star contains. A small shift towards red or blue can reveal whether an object is moving away or towards us. The distortion of distant light can reveal the gravitational influence of matter that may itself be invisible. Light also carries energy. Sunlight warms the ground because electromagnetic energy is absorbed and redistributed among atoms and molecules. Solar panels convert part of that energy into electrical current. Plant cells capture some of it through photosynthesis, using light to support chemical reactions that store energy in sugars. Most ecosystems on Earth depend, directly or indirectly, on this continuing flow of sunlight. Light also carries momentum even though photons have no rest mass. This may sound contradictory at first, because everyday objects usually possess momentum because they have mass and motion. Photons, however, belong to the quantum description of the electromagnetic field. They always travel at the speed of light in vacuum and can transfer momentum when they interact with matter. The pressure produced by ordinary light is usually tiny, but it is real. It can be measured in laboratories and can influence particles in space. Proposals for solar sails use the momentum of sunlight to push extremely light spacecraft over long periods. The force is gentle, but space provides plenty of time for gentle forces to become useful. The word photon can make light sound like a stream of tiny luminous beads. That picture is sometimes helpful, but it is not complete. Light also produces interference and diffraction, behaviours associated with waves. It can spread through openings, overlap with itself and create alternating regions of reinforcement and cancellation. For centuries, physicists debated whether light was made of particles or waves. Isaac Newton developed a particle-like theory of light. Christian Huygens argued for a wave description. Thomas Young's interference experiments provided powerful evidence for waves. James Clerk Maxwell later showed that light could be understood as an electromagnetic wave. Then Max Planck and Albert Einstein helped reveal that light exchanges energy in discrete quantum amounts. None of these stages can be reduced to a simple story in which one side was entirely foolish and the other entirely correct. Geometric rays remain useful for mirrors and lenses. Classical waves explain interference, diffraction, and polarization. Electromagnetic fields describe how light propagates. Photons describe quantized emission, absorption, and detection. Quantum field theory connects these ideas more deeply by treating photons as excitations of the electromagnetic field. The apparent contradictions arise mainly when one model is asked to explain everything. A ray is not a literal physical stick moving through space. A classical wave is not always sufficient to describe individual detection events. A photon is not an ordinary microscopic ball. Each description captures particular aspects of light under particular conditions. This layered understanding is common in physics. A map of a city may show roads, another may show railways, and another may show elevation. The maps look different because they answer different questions. Their differences do not mean the city changes identity whenever someone unfolds a new piece of paper. Light behaves in ways that require several connected descriptions because nature is not obliged to resemble the objects of everyday experience. It does not have to be either a water wave or a flying grain of sand. Those are familiar categories created from the human-scale world. Light belongs to a deeper physical framework, and yet this strange phenomenon is constantly present. It falls across tables, glimmers on water, and carries the colours of familiar faces. It links the smallest quantum interaction to the largest visible structures in the universe. Through light, matter becomes visible, distant history becomes observable, and the laws of physics reveal themselves one photon at a time. Long before light was described through electromagnetic fields or photons, people had already noticed that it seemed to travel in orderly ways. Shadows formed sharp boundaries. Mirrors returned recognizable images. Sunlight passing through a small gap created a bright patch on the opposite wall. These ordinary effects suggested that light followed paths which could be studied with lines, angles, and geometry. The earliest theories of vision did not all begin from the same assumption. Some ancient Greek thinkers believed that sight occurred because something travelled outward from the eyes and touched the objects being observed. This idea is often called emission theory. It may now seem unusual, but it arose naturally from the feeling that vision is active, as though the gaze reaches into the world. Other thinkers proposed that objects somehow released copies or impressions of themselves. The central difficulty was deciding which way the influence travelled. Did the eye send something outward, or did light enter the eye from the surrounding world? Euclid, writing in ancient Greece, developed a geometric description of vision using straight lines extending from the eye. His treatment was not a correct physical account of how sight works, but the geometry itself was extremely valuable. It provided ways to reason about apparent size, direction, perspective, and reflection. Several centuries later, Ptolemy developed geometrical optics further. He studied reflection and refraction, measured angles, and examined how light changes direction when passing between substances such as air and water. His explanations still included ideas about visual rays emerging from the eye, yet his systematic use of geometry helped establish a language that optics continues to use. The decisive correction came much later through the work of the Arab physicist and mathematician Ibn al-Haytham, known in medieval Europe as al-Haytham. Working around the late 10th and early 11th centuries, Ibn al-Haytham argued that vision occurs when light reflected from objects enters the eye. This reversed the direction assumed by emission theories. The eye did not illuminate or physically reach towards an object. Light travelled from a source, interacted with the object, and then entered the eye. Ibn al-Haytham presented his ideas in the Book of Optics, a major work covering vision, reflection, refraction, lenses, and the behaviour of light. His importance came not only from the conclusions he reached, but also from the methods he used. He relied on observation, controlled tests, and deliberate attempts to separate possible explanations. One of his most famous demonstrations involved a darkened room with a small opening in one wall. Light from the outside passed through the opening and formed an inverted image on the opposite surface. This arrangement is now called a camera obscura, meaning a dark chamber. The image formed because light from different parts of the outdoor scene travelled along different paths through the narrow opening. Light from the upper part of an object reached the lower part of the image, while light from the lower part reached the upper part. The opening allowed only a limited range of paths to pass through, producing an image without a lens. This offered powerful evidence that light travels approximately in straight lines through a uniform medium. If light wandered freely around corners in ordinary conditions, the image would blur into a general patch of brightness. The straight line model remains one of the foundations of geometric optics. Light is represented using rays, which indicate the direction in which energy travels. These rays are not tiny solid rods or glowing threads. They are mathematical constructions used to trace paths through optical systems. This simple model explains a remarkable amount. A shadow forms when an opaque object blocks rays travelling from a source. A solar eclipse occurs when the moon blocks direct sunlight from reaching part of Earth. A lunar eclipse occurs when the moon moves through Earth's shadow. The sharpness of a shadow depends partly on the size of the light source. A very small source can produce a relatively sharp boundary. A large source, such as the Sun, creates a darker central region called the umbra, and a lighter outer region called the penumbra. Different parts of the extended source remain visible from different positions near the edge of the shadow. Reflection can also be described geometrically. When a ray reaches a smooth surface, the angle at which it arrives equals the angle at which it leaves. These angles are measured relative to an imaginary line perpendicular to the surface, called the normal. This rule is known as the law of reflection. It explains why a flat mirror creates an organized image. Rays reaching the mirror are redirected in a consistent pattern. When those reflected rays enter the eyes, they appear to come from positions behind the mirror. Most objects are not smooth enough to act like mirrors. A wall may appear flat to a hand, yet its surface is irregular on microscopic scales. Incoming light is reflected in many directions. This process is called diffuse reflection. Diffuse reflection is why an ordinary object can be seen from many different positions. Light reaches the surface and is scattered towards observers across a wide range of angles. A polished surface produces specular reflection, preserving enough directional organization to create a clear image. Both processes obey the law of reflection locally. The difference lies in the orientation of the tiny surface regions. On a mirror, these regions are closely aligned. On a rough surface, they point in many directions. Geometric optics became essential to the development of mirrors, lenses, cameras, microscopes, and telescopes. Designers can trace rays through curved glass or reflective surfaces to predict where an image will form and how large it will appear. The model is elegant, practical, and often extremely accurate. Yet it is not the final description of light. When light passes through openings comparable to its wavelength, it spreads through diffraction. When light is detected in individual quantum events, the idea of a simple continuous ray becomes incomplete. The early science of optics nevertheless established something fundamental. Light behaves with enough order that its paths can be studied, measured, and predicted. From shadows on a wall and images inside darkened rooms, a precise science began to emerge. The straight rays of geometric optics are wonderfully useful, but they leave a deeper question unanswered. What is actually travelling along those paths? By the 19th century, physicists had begun to understand that electricity and magnetism were not isolated curiosities. They were connected parts of a wider physical system, capable of producing forces across space and changing one another in precise, measurable ways. An electric field describes the influence that electric charges create in the space around them. Place another charged object within that region, and it experiences a force. A magnetic field describes the influence associated with magnets, electric currents, and moving charges. These fields are not merely lines drawn in a textbook. The lines are visual aids, while the fields themselves represent physical conditions distributed throughout space. One of the central figures in uncovering their relationship was the English scientist Michael Faraday. Faraday had relatively little formal mathematical education, but he possessed an extraordinary experimental imagination. He explored electricity and magnetism through coils, wires, batteries, magnets, and carefully arranged apparatus. In 1831, Faraday demonstrated electromagnetic induction. He showed that a changing magnetic field can produce an electric current. A stationary magnet beside a stationary coil did little, but moving the magnet or changing the magnetic environment created a current in the wire. This revealed that electricity and magnetism were dynamically linked. A changing magnetic condition could create an electric effect. Faraday also helped connect electromagnetism with light. In 1845, he discovered that a magnetic field could rotate the plane of polarization of light passing through certain materials. Polarization describes the orientation of the electric oscillation associated with a light wave. The discovery, now called the Faraday effect, showed that magnetism could directly influence light. This was a profound clue. Electricity, magnetism, and optics were not separate territories after all. Faraday imagined fields using lines of force extending through space. His ideas were physically insightful, but they still lacked a complete mathematical framework. That framework was developed by the Scottish physicist James Clerk Maxwell. During the 19th century, Maxwell brought together earlier laws describing electric charges, electric currents, magnetic fields, and electromagnetic induction. The resulting system became known as Maxwell's equations. These equations describe how electric charges create electric fields, how electric currents create magnetic fields, how changing magnetic fields generate electric fields, and how changing electric fields generate magnetic fields. The last relationship was especially important. Maxwell realized that a changing electric field could create a magnetic field even in a region where no ordinary current flowed. This completed the symmetry of the theory and allowed something remarkable to happen. Imagine an electric field changing through space. That changing electric field produces a magnetic field. The magnetic field also changes, producing another electric field farther on. The disturbance can continue sustaining itself, with changing electric and magnetic fields repeatedly generating one another as they move. The result is an electromagnetic wave. When Maxwell calculated the predicted speed of this wave, he obtained a value close to the measured speed of light. The agreement was far too striking to dismiss as coincidence. Maxwell concluded that light itself was an electromagnetic wave. Visible light was no longer understood merely as something that followed geometric paths. It was a travelling disturbance in electric and magnetic fields. In a simplified electromagnetic wave, the electric field oscillates in one direction, while the magnetic field oscillates in a direction perpendicular to it. Both are also perpendicular to the direction in which the wave travels. Textbooks often represent this using two smooth repeating curves. One curve may rise and fall vertically, while another oscillates sideways. These drawings are helpful, but they can easily create the wrong mental picture. Light does not usually snake through space along a wavy track. The curves represent how the strengths and directions of the electric and magnetic fields vary from place to place and moment to moment. The direction of travel can remain straight even while the field values oscillate. Several properties are used to describe a wave. Wavelength is the distance between corresponding points in successive cycles, such as one peak and the next. Frequency is the number of complete oscillations passing a point during a given interval of time. Amplitude describes the maximum strength of the oscillation. In many ordinary situations, greater amplitude corresponds to greater intensity, meaning more energy passing through a given area each second. Phase describes the position within the repeating cycle. Two waves with matching phases rise and fall together. Waves with different phases may reinforce one another in some places and cancel one another in others. Wavelength and frequency are connected because a wave travelling at a fixed speed covers one wavelength during each cycle. The speed of light equals wavelength multiplied by frequency. This relationship applies across the electromagnetic spectrum. A wave with a longer wavelength has a lower frequency, while a shorter wavelength corresponds to a higher frequency, provided both travel at the same speed in vacuum. Maxwell's theory made a bold prediction. If visible light was electromagnetic radiation, then electromagnetic waves with much longer wavelengths should also exist. The German physicist Heinrich Hertz tested this prediction during the late 19th century. He produced rapidly changing electric currents that generated radio waves, and detected those waves using a separate loop of wire. Tiny sparks in the detector showed that electromagnetic energy had crossed the room without a physical connection. Hertz demonstrated that the waves could reflect, refract, interfere, and become polarized, just as Maxwell's theory predicted. Radio waves and visible light were different regions of the same electromagnetic spectrum. Unlike sound, electromagnetic waves do not require a material medium. Sound travels through the vibrations of atoms and molecules in air, water, or solids. Remove the material, and ordinary sound has nothing through which to propagate. A wave on a rope similarly depends on the rope itself. The disturbance moves because neighbouring sections pull upon one another. Electromagnetic waves are different. Their changing electric and magnetic fields can propagate through a vacuum. This is why sunlight can cross the nearly empty space between the Sun and Earth. There is no need for an invisible cosmic rope, which is fortunate because storing one would be inconvenient. The wave description explains why light can interfere, producing bright and dark patterns when waves overlap. It explains diffraction, where light spreads after passing through a narrow opening. It accounts naturally for polarization, and provides a deeper basis for reflection and refraction at boundaries between materials. Geometric rays remain useful whenever the wavelength is extremely small compared with the objects and openings involved. Yet the electromagnetic wave reveals what the ray model leaves hidden. The paths traced by optics are paths followed by changing fields, carrying energy across space at the speed of light. Maxwell's theory revealed that light is an electromagnetic wave, but it also raised a remarkable question. How fast does that wave travel? In a vacuum, light moves at approximately 299,792 kilometers per second. At that speed, light could travel around Earth more than 7 times in a single second. It crosses the distance from the Moon to Earth in a little over 1 second and reaches Earth from the Sun in a little more than 8 minutes. The speed is enormous, but it is not infinite. Galileo Galilei made one of the earliest recorded attempts to measure it. He proposed placing 2 observers on distant hills, each carrying a covered lantern. One observer would uncover a lantern, and the second would uncover another as soon as the first flash became visible. By measuring the delay, Galileo hoped to determine how long light took to travel between them. The experiment could not succeed over such a short distance. Human reaction times were far longer than the travel time of light between nearby hills. Galileo could only conclude that light was either instantaneous or much faster than he could measure. A more convincing answer came from astronomy. During the 17th century, the Danish astronomer Ole Rømer studied Io, one of Jupiter's moons. Io moves around Jupiter with a regular orbital period and repeatedly passes into Jupiter's shadow. These eclipses could be predicted like the ticking of a distant clock. Rømer noticed that the eclipses appeared later than expected when Earth was moving farther from Jupiter and earlier when Earth was moving closer. The Moon itself was not changing its orbit in a way that matched the pattern. Instead, the changing delay was caused by the varying distance that light had to travel. When Earth was on the more distant side of its orbit, light from Jupiter required additional time to reach observers. Rømer's result provided the first strong evidence that light travels at a finite speed. Later experiments brought the measurement down from astronomical distances to laboratories on Earth. In the 19th century, The French physicist Hippolyte Fizeau sent light through the gaps of a rapidly rotating toothed wheel towards a distant mirror. The returning light could either pass through the next gap or be blocked by a tooth, depending on the speed of the wheel. By combining the wheel's rotation rate with the distance travelled, Fizeau estimated the speed of light. Léon Foucault refined the method using a rotating mirror. Albert Michelson later improved rotating mirror experiments still further, using longer paths and more precise instruments. The measured values moved steadily closer to the modern result, yet the growing accuracy created a deeper puzzle. Sound waves require air or another material. Water waves require water. Since light had been identified as a wave, many physicists assumed it must also travel through some medium. This hypothetical substance became known as the luminiferous ether. The ether was imagined as filling all of space while remaining invisible and almost impossible to disturb. Earth should move through it while orbiting the Sun, creating an ether wind. Light travelling with or against that wind should then appear to move at slightly different speeds. Albert Michelson and Edward Morley designed an interferometer to detect this difference. Their experiment in 1887 split a beam of light along two perpendicular paths, reflected both beams back, and recombined them. Any difference in travel time should have shifted the interference pattern. The expected shift did not appear. The Michelson-Morley experiment failed to detect Earth's motion through the ether. Other explanations were proposed, including physical contraction along the direction of motion, but the old picture of a simple mechanical light-carrying medium became increasingly difficult to preserve. In 1905, Albert Einstein introduced the special theory of relativity. One of its central principles was that the speed of light in a vacuum is the same for every inertial observer, regardless of the motion of the light source or the observer. This is unlike ordinary motion. If a train moves forwards and a passenger throws a ball in the same direction, someone standing beside the tracks measures the ball's speed as the train's speed plus the speed of the throw. Light does not follow that simple rule. A person moving towards a light beam and a person moving away from it both measure the same vacuum speed of light. Nature preserves that speed by allowing measurements of space and time to depend on relative motion. Moving clocks run slowly when compared from another inertial frame. This effect is called time dilation. Distances along the direction of motion become shorter in that frame, producing length contraction. Events that one observer judges to be simultaneous may occur at different times for another observer, creating the relativity of simultaneity. These are not visual tricks caused by slow signals or poor clocks. They are physical consequences of the structure of space-time. The speed of light acts as the conversion factor linking space and time. It is also the maximum speed at which information and causal influence can propagate through vacuum. Light does move more slowly through transparent materials such as water or glass. The reduction arises because the electromagnetic field interacts with charged particles in the material. The resulting propagation of the combined disturbance differs from propagation through empty space. The fundamental vacuum speed itself remains unchanged. Photons have no rest mass and always propagate at the speed of light when travelling freely through vacuum. Objects with rest mass behave differently. Accelerating them requires increasing amounts of energy, and the energy needed rises without limit as their speed approaches the speed of light. They can move extremely quickly, but they cannot be accelerated all the way to that boundary. Because light has a finite speed, every observation of the universe is also an observation of the past. The moon is seen as it was a little over 1 second ago. The sun appears as it was more than 8 minutes ago. The nearest large galaxy is seen as it was more than 2 million years in the past. Light does not merely move through space and time. Its constant speed helps define how space and time fit together, setting the causal structure of the universe and placing every distant object behind a small curtain of travel time. Light can travel across a room, through a glass lens or between distant stars, but before it can travel anywhere, it must first be produced. At the broadest level, electromagnetic radiation is emitted when charged particles accelerate or when quantum systems change from one energy state to another. These two descriptions often overlap. Matter contains electrically charged particles, and changes in their motion or energy can disturb the electromagnetic field, releasing energy as radiation. One familiar source is thermal radiation. Every object with a temperature above absolute zero contains moving particles. Atoms vibrate, molecules rotate, and charged particles shift within matter. This restless microscopic motion produces electromagnetic radiation. The distribution of wavelengths depends strongly on temperature. A person, a table, and the walls of a room all emit radiation, but most of it lies in the infrared region and cannot be seen by human eyes. A thermal camera detects part of this invisible emission and converts it into a visible image. Physicists often describe thermal emission using the idea of a blackbody. A perfect blackbody is an idealized object that absorbs all radiation falling upon it and emits radiation with a spectrum determined only by its temperature. No real object is perfectly black in this technical sense, although stars, heated cavities, and many hot materials can behave approximately like black bodies across useful ranges of wavelength. As an object becomes hotter, its visible appearance changes. Warm objects radiate mainly infrared light. Heat a piece of metal sufficiently and it begins to glow dull red. At higher temperatures it becomes orange, yellow, and eventually white. Extremely hot objects may appear blue-white because their emission is stronger at shorter wavelengths. Wien's displacement law describes this shift. As temperature rises, the wavelength at which thermal emission is strongest becomes shorter. This is why relatively cool stars tend to appear reddish, while hotter stars often appear white or blue. Temperature also changes the total amount of radiation produced. The Stefan-Boltzmann law states that the energy emitted from each unit of surface area rises in proportion to the fourth power of absolute temperature. Doubling the absolute temperature therefore increases the emitted power by a factor of 16. Hot objects do not merely change colour, they become dramatically more radiant. Light can also be produced through transitions between quantum energy levels. Electrons bound within atoms cannot possess just any energy, they occupy allowed states. When an electron moves from a higher energy state to a lower one, the atom may release the energy difference as a photon. Because each chemical element has its own arrangement of energy levels, it can emit particular wavelengths. This produces characteristic spectral lines. Hydrogen, neon, sodium, and other elements each create distinct optical signatures, allowing scientists to identify substances in laboratories, flames, nebulae, and distant stars. A gas discharge lamp uses this principle. An electric current excites atoms in a gas, and those atoms emit light as their electrons return to lower energy states. A neon sign glows because excited neon atoms release a set of characteristic reddish-orange wavelengths. Other gases produce different colours. Fluorescence also begins with absorption. A material absorbs higher energy light and quickly re-emits part of that energy at a longer wavelength. The process usually ends almost immediately when the source is removed. Phosphorescence involves longer-lived excited states. Energy becomes temporarily trapped in arrangements from which the return to a lower state is less likely. The material can therefore continue glowing for seconds, minutes, or sometimes longer after illumination ends. Light-emitting diodes produce light through electroluminescence. Inside a semiconductor, electrical energy brings electrons and electron vacancies, commonly called holes, together. When they recombine, energy can be released as photons. The the color depends largely on the semiconductor's band gap, while modern device design allows light-emitting diodes to produce many colors efficiently. Lasers use a more organized process called stimulated emission, anticipated by Albert Einstein in the early 20th century. An incoming photon can encourage an excited atom or molecule to release another photon with matching frequency, phase, and direction. For this to build into a powerful beam, the laser medium requires a population inversion, meaning that more particles occupy an excited state than would normally be expected. Mirrors form an optical cavity around the material, causing light to pass through repeatedly and stimulate further emission. One mirror allows a small fraction to escape as the laser beam. Different sources therefore produce very different kinds of light. Thermal sources emit broad ranges of wavelengths in many directions with largely unrelated phases. Discharge lamps produce stronger spectral lines, associated with particular atoms. Light-emitting diodes convert electrical energy efficiently into selected wavelength ranges. Lasers can produce highly directional, narrow and coherent beams whose waves maintain controlled phase relationships. The same principles appear throughout nature. Stars shine largely through thermal radiation, powered by nuclear fusion in their interiors. Nebulae glow as excited atoms and ions release photons. Lightning accelerates charges through the atmosphere. Auroras form when energetic particles from space excite atoms and molecules high above Earth. Whether light comes from a candle, a screen, a storm, or a star, its production reflects the same deeper pattern. Charged matter changes, energy is rearranged, and the electromagnetic field carries part of that energy away. Once light has been produced, its journey is shaped by whatever it encounters. A beam crossing empty space may continue undisturbed, but the moment it reaches matter, several different outcomes become possible. It may be absorbed, transmitted, reflected, or scattered. In many real materials, more than one of these processes occurs at the same time. Matter is made from charged particles. Atomic nuclei carry positive charge, electrons carry negative charge, and both can respond to an incoming electromagnetic field. The details depend on the structure of the material and on the wavelength, frequency, energy, and momentum carried by the light. Absorption occurs when electromagnetic energy is transferred into matter. In a quantum description, a photon can be absorbed only when the material has an available process capable of accepting the required energy and momentum. That process may involve an electron moving to a higher energy state, a molecule beginning to rotate or vibrate more strongly, or a collective excitation spreading through a solid. This selectivity is why a material can absorb one range of wavelengths while allowing another to pass. Transparency is never a completely universal property. A sheet of ordinary glass is transparent to much of visible light, but it absorbs significant amounts of ultraviolet radiation and parts of the infrared spectrum. A substance that appears clear to the human eye may therefore be quite opaque to a detector operating at another wavelength. When light passes through a material without being strongly absorbed or scattered, the result is transmission. The electromagnetic wave still interacts with charged particles inside the substance, but those interactions do not permanently remove most of its energy. Instead, the material responds and contributes to the way the disturbance propagates. This is why transmitted light can travel more slowly through glass or water than through a vacuum. It is not simply slipping between atoms while occasionally becoming delayed. The electric field of the light drives charges within the material, and their collective response changes the speed and direction of the combined electromagnetic disturbance. Reflection is another consequence of this interaction. At the microscopic level, light does not strike a perfectly rigid wall and bounce away like a rubber ball. The incoming electromagnetic field causes electrons within the surface to move. Those accelerated charges generate electromagnetic radiation of their own. The combined response of enormous numbers of charged particles produces reflected wave travelling away from the surface. The organisation of the material determines whether that reflection forms a clear image. In polished metal or smooth glass, neighbouring regions of the surface redirect the light in a highly coordinated way. This produces specular reflection. A rough wall also reflects light, but its uneven microscopic surfaces send the light in many directions, producing diffuse reflection. Metals are particularly reflective across much of the visible spectrum because they contain mobile conduction electrons. These electrons respond strongly to incoming electric fields and collectively generate radiation that largely cancels the field inside the metal while producing a strong reflected wave outside it. This response is not identical at every frequency. Some metals absorb selected wavelengths more strongly than others. Gold reflects red and yellow wavelengths efficiently, but absorbs more blue light, giving it its characteristic warm colour. Silver reflects most visible wavelengths relatively evenly, which is why it appears bright and nearly colourless. Insulating materials behave differently because their electrons are more tightly bound. In glass, many visible photon energies do not match available electronic transitions, so visible light is not strongly absorbed. Higher energy ultraviolet photons can interact with electronic states, while lower energy infrared radiation may excite molecular vibrations. The same sheet of glass can therefore be transparent, absorbing or reflective depending on the wavelength. Scattering redirects light without necessarily removing all of its energy from the electromagnetic field. It can occur when light interacts with molecules, particles, surface irregularities, or fluctuations inside a material. The redirected light may retain the same frequency, or it may exchange a small amount of energy with the matter and emerge at a different frequency. A clear pane of glass transmits much of the visible light falling upon it because absorption and internal scattering are weak. Frosted glass is made from essentially similar material, but its rough surface and internal irregularities scatter light in many directions. It still transmits illumination, yet organized images become blurred. This illustrates the difference between transparency and translucency. A transparent material allows light to pass with enough directional order to preserve a clear image. A translucent material transmits light but scatters it strongly. An opaque material prevents significant transmission because the light is mainly absorbed, reflected, or scattered back. Dark fabric in sunlight absorbs much of the visible and infrared radiation that reaches it. The absorbed energy is transferred into molecular vibrations and microscopic motion, increasing the material's thermal energy. This is why dark clothing can become warmer than pale clothing under the same illumination. Absorbed energy does not simply vanish. It may be stored briefly in an excited electronic state, used in a chemical reaction, or converted into heat. In ordinary materials, much of it is eventually redistributed among countless atomic and molecular motions, and later emitted as longer wavelength thermal radiation. Coloured filters provide another clear example. A red filter does not add redness to white light. It transmits a range of red wavelengths while absorbing or reflecting much of the rest. A green leaf appears green for a similar reason. Pigments within the leaf absorb strongly in parts of the red and blue regions while reflecting and transmitting more green light. Sunscreen relies on wavelength-dependent interaction as well. Its active ingredients absorb, reflect, or scatter ultraviolet radiation before too much of that energy reaches living skin cells. A sunscreen may remain nearly transparent in visible light while behaving very differently at shorter ultraviolet wavelengths. Throughout every one of these processes, energy and momentum are conserved. If light loses energy, the matter must gain it, or another form of radiation must carry it away. If a photon changes direction, momentum must also be transferred between the light and the material. Nothing visible has a colour, brightness, or texture entirely by itself. Appearance emerges from an interaction between the spectrum of the illumination, the microscopic structure of the material, and the detector observing the result. A polished metal surface, a frosted window, a black shirt, and a coloured filter all look different because each selects, redirects, and absorbs light in its own wavelength-dependent way. The visible world is therefore not made merely from objects waiting passively to be seen. It is created through a continuous exchange between electromagnetic fields and matter, repeated across every surface, every molecule, and every moment of illumination. The visible world seems to be filled with colour, yet colour begins with something that has no colour in the ordinary human sense. Electromagnetic radiation arrives with particular wavelengths, frequencies, and energies. Matter responds to those wavelengths selectively, and the nervous system turns the resulting signals into the experience of red, green, blue, and every shade between them. Visible light occupies only a narrow region of the electromagnetic spectrum. Human vision is most sensitive to wavelengths from roughly 400 to 700 nanometers, although the boundaries are not perfectly sharp. Sensitivity fades gradually towards the ultraviolet at the shorter end and the infrared at the longer end. A nanometer is 1/1000th of a meter. Visible wavelengths are therefore tiny, yet they are still much longer than the dimensions of individual atoms. Violet light lies near the shorter wavelength end of human vision, while red light lies near the longer wavelength end. Wavelength describes the distance over which an electromagnetic wave completes one full cycle. Frequency describes how many cycles pass a point during a given interval of time. Because light in a vacuum travels at a fixed speed, the two are linked. The speed of light equals wavelength multiplied by frequency. A longer wavelength must therefore have a lower frequency, while a shorter wavelength must have a higher frequency. Photon energy also depends on frequency. The energy of a photon equals Planck's constant multiplied by frequency. This means that shorter wavelength light carries more energy per photon than longer wavelength light. A violet photon carries more energy than a red photon. An ultraviolet photon carries more than either, while X-ray and gamma-ray photons carry still more. The connection between light and colour became much clearer through the experiments of Isaac Newton. In the 17th century, Newton allowed a narrow beam of sunlight to enter a darkened room and pass through a glass prism. The emerging light spread into a band of colours ranging from red through orange, yellow, green, and blue to violet. At the time, some people believed the prism might be adding colour to otherwise pure white light. Newton tested this idea by isolating one colour and passing it through another prism. The selected colour could bend again, but it did not split into a new range. He then used a second prism to recombine the separated colours into white light. The prism was not manufacturing colour. White sunlight already contained a broad mixture of visible wavelengths. The separation occurs because the refractive index of glass depends on wavelength. Different wavelengths travel through the material in slightly different ways and are bent through different angles. This wavelength-dependent refraction is called dispersion. Red light is generally bent less strongly by ordinary glass than violet light. The prism spreads the incoming mixture into a continuous spectrum. That word continuous is important. Nature does not divide visible light into a few perfectly separated bands. The familiar colour names are convenient categories applied to a smooth range of wavelengths. There is no physical line where orange suddenly stops and yellow begins. The transitions blend gradually. The boundaries of the entire electromagnetic spectrum are also conventional. Move beyond the red end of visible light and the radiation becomes infrared. Continue to longer wavelengths, and the named regions include microwaves and radio waves. Infrared radiation is strongly associated with thermal emission from objects at everyday temperatures. Microwaves interact effectively with rotations and collective motions in certain molecules and materials. Radio waves can extend from wavelengths shorter than a person to wavelengths longer than buildings, landscapes, or even planets. Move beyond the violet end, and the radiation becomes ultraviolet. At still shorter wavelengths like X-rays and gamma rays, these regions do not contain fundamentally different forms of light. They are all electromagnetic radiation. The names simply group ranges that tend to be produced, detected, or used in different ways. The difference between them becomes especially important when radiation interacts with matter. Photon energy can determine whether a particular physical or chemical process is possible. Visible photons can excite electronic transitions in certain molecules, including the pigments used by the eye. Ultraviolet photons can trigger stronger chemical changes and damage biological tissue. At sufficiently high energies, photons can remove electrons from atoms entirely. This process is called ionization. Brightness alone cannot always compensate for insufficient photon energy. A very intense beam of low-energy radiation may deliver a large amount of total energy, but each photon may still be unable to initiate a particular molecular transition. A smaller number of higher-energy photons may be able to do so. This is why the energy of individual photons matters in processes such as the photoelectric effect, photochemistry, and radiation damage. The total amount of light and the energy carried by each photon are related but distinct properties. Visible wavelength is not the same thing as perceived colour. A nearly pure wavelength can produce a colour sensation, but many familiar colours do not correspond to any single wavelength. Purple often results from a mixture that stimulates both the short wavelength and long wavelength parts of human colour vision. Magenta is another non-spectral colour, commonly produced by combining red and blue or violet light. There is no isolated magenta wavelength between red and violet in the physical spectrum. White is normally produced by a broad mixture of wavelengths, or by selected combinations that stimulate the three cone classes in a balanced way. Brown is usually perceived when an orange or yellowish region appears relatively dim compared with its surroundings. Its appearance depends strongly on context, brightness, and contrast. The eye does not contain a miniature spectrometer that identifies every wavelength separately. Human colour vision begins with three main classes of cone photoreceptors, each with a broad and overlapping range of sensitivity. The brain compares their responses and constructs colour from the pattern. Different mixtures of wavelengths can therefore produce the same cone responses and appear identical. This phenomenon is called metamerism. A patch on a screen in a painted surface may look like the same yellow, even though the physical combinations of wavelengths reaching the eye are quite different. To describe real light sources accurately, scientists often use a spectral power distribution. This shows how much energy a source emits or reflects across different wavelengths. Sunlight has a broad and relatively continuous visible distribution, modified by absorption within the Sun and Earth's atmosphere. An incandescent lamp also produces a broad spectrum, but with more energy concentrated towards longer wavelengths. A fluorescent lamp or some light-emitting diodes may produce several distinct peaks. A laser may emit within a very narrow wavelength range. Objects also have wavelength-dependent reflectance. A leaf appears green because its pigments and internal structure absorb some wavelengths more strongly while reflecting or transmitting more of the green region. A red surface reflects more long-wavelength visible light under suitable illumination. The phrase "under suitable illumination" matters. A red object placed under blue light may appear very dark because little red light is present for it to reflect. The apparent colour of an object depends on both its material properties and the spectrum of the light falling upon it. Colour is therefore created by a chain of physical and biological events. A source emits a distribution of wavelengths. Matter absorbs, reflects, scatters, or transmits them selectively. The eye samples the remaining light through its photoreceptors, and the brain interprets those signals in relation to brightness, context, and previous experience. The physical spectrum constrains what can be seen, but it does not arrive already divided into the colours of human experience. Those colours emerge when electromagnetic radiation meets matter, biology, and perception. Reflection and refraction are among the most familiar behaviours of light. A face appears in a mirror, a spoon seems displaced in a glass of water, and a swimming pool looks shallower than it really is. These effects can be described with simple raised angles, but beneath that geometry lies the interaction between electromagnetic fields and matter. Reflection begins when incoming light reaches a boundary. In geometric optics, the arriving path is called the incident ray, and the departing path is called the reflected ray. To describe the angles clearly, an imaginary line called the normal is drawn perpendicular to the surface at the point where the light arrives. The law of reflection states that the angle of incidence equals the angle of reflection. Both angles are measured from the normal rather than from the surface itself. A smooth mirror preserves the organisation of incoming wavefronts. Light arriving from one point on an object is redirected in a consistent pattern, so the reflected rays appear to originate from a corresponding point behind the mirror. The image is virtual because the reflected light does not actually converge at that apparent location. At the microscopic level, the process is more subtle than a tiny ball rebounding from a wall. The electric field of the incoming light drives charged particles within the material. Their collective electromagnetic response produces new radiation. Some of that radiation travels back into the original medium as the reflected wave. When light passes into another transparent material, it may also change direction. This is refraction. The amount of bending depends on the refractive indices of the two materials and on the angle at which the light reaches the boundary. Refractive index describes how the propagation of light in a material differs from its propagation in vacuum. The relationship is expressed by Snell's law, named after the Dutch mathematician Willebrord Snellius. The refractive index of the first material multiplied by the sine of the incident angle equals the refractive index of the second material, multiplied by the sine of the refracted angle. When light enters a material with a higher refractive index at an angle, it usually bends towards the normal. When it enters a material with a lower refractive index, it usually bends away from the normal. This explains why a straw appears bent where it enters water. Light reflected from the submerged part changes direction as it passes from water into air. The brain traces the arriving rays backwards along straight paths, placing the submerged section at an apparent position different from its true one. A swimming pool appears shallower for the same reason. Light from the bottom refracts at the water's surface, causing the floor to appear raised. The water has not politely moved the bottom closer. The light has simply changed direction before reaching the observer. It is common to say that light bends because it slows down inside the material. That statement is useful but incomplete. The electromagnetic field interacts continuously with charged particles throughout the medium. Their response changes the propagation of the combined disturbance. The light does not pause at the boundary, make a small decision, and then select a new route. A deeper way to describe optical paths comes from the principle associated with the French mathematician Pierre de Fermat. Fermat's principle states that light follows a path for which the travel time is stationary, relative to nearby possible paths. In many ordinary situations, this path is the one requiring the least time. However, the The more precise word is stationary, because the travel time is not always a simple absolute minimum. Fermat's principle can reproduce both reflection and refraction, and explains why a bent route through two materials may take less time than a geometrically shorter one. Different wavelengths can experience slightly different refractive indices within the same material. This wavelength dependence is called dispersion. A prism separates white light, because violet wavelengths are generally refracted more strongly than red wavelengths in ordinary glass. The same principle contributes to rainbow formation, where sunlight is refracted, internally reflected and dispersed inside water droplets. Dispersion also causes chromatic aberration in simple lenses. Different colours are brought to focus at slightly different positions, producing coloured fringes and reducing image sharpness. Optical designers correct this by combining materials and lens shapes with different dispersive properties. Gemstones sparkle partly because of strong refraction, dispersion, and repeated internal reflections. A well-cut diamond redirects light through many paths, separates some wavelengths, and sends flashes back towards the observer. It is a rather elaborate use of geometry for a small piece of carbon. Another important effect occurs when light attempts to move from a material with a higher refractive index into one with a lower refractive index. Beyond a particular angle, known as the critical angle, no ordinary transmitted ray emerges. Instead, the light is reflected back inside the material. This is total internal reflection. The effect can confine light within glass or transparent plastic, even when the material bends. Optical fibres use a central core surrounded by material with a slightly lower refractive index. Light entering within the permitted range of angles remains guided along the core through repeated total internal reflection, though a more complete wave description also includes guided electromagnetic modes. Optical fibres carry enormous amounts of digital information across cities, countries and oceans. Different wavelengths can transmit separate streams of data through the same fibre, allowing modern communication networks to move vast quantities of information with relatively low loss. Bundles of fibres are also used in medical endoscopes, carrying illumination into the body and returning optical information from places that would otherwise be difficult to observe. Curved surfaces use refraction to form images. A converging lens is thicker near the centre and redirects parallel incoming rays towards a focal point. The distance between the lens and that focus is called the focal length. A diverging lens spreads parallel rays outward. Those rays appear to originate from a virtual focal point on the same side of the lens as the incoming light. A real image forms where rays physically converge and can be projected onto a screen. A virtual image forms where rays only appear to originate or converge when traced backwards. Magnifying glasses, cameras, microscopes, telescopes, and the human eye all depend on controlled combinations of these effects. Corrective lenses compensate for focusing problems in vision. A diverging lens can help correct short-sightedness, while a converging lens can help correct long-sightedness, guiding light so that a clear image forms on the retina. Refraction can also occur gradually rather than at a single boundary. In a mirage, layers of air at different temperatures have slightly different refractive indices. Light follows a curved path through the changing atmosphere, sometimes creating the appearance of water on a hot road, or displacing the apparent position of a distant object. Mirrors, lenses, fibres and prisms reveal what happens when light meets carefully controlled surfaces. The same laws also operate in air filled with temperature gradients, droplets, dust and ice crystals, where the atmosphere turns ordinary sunlight into colours, halos and shifting images across the sky. The atmosphere is almost transparent, yet it transforms sunlight into one of the most familiar colour displays on Earth. During the day, the sky appears blue. Near sunset, the same sun may turn yellow, orange or deep red. Clouds remain pale, distant hills fade into haze, and rain sometimes separates sunlight into a curved spectrum. These effects emerge from scattering, refraction, and the wavelength-dependent behavior of light. Sunlight entering Earth's atmosphere interacts with molecules of nitrogen and oxygen, along with smaller contributions from other gases. These molecules are much smaller than visible wavelengths. Their influence is described by Rayleigh scattering, named after the British physicist John William Strutt, better known as Lord Rayleigh. Rayleigh scattering redirects shorter visible wavelengths much more strongly than longer ones. Its strength varies approximately as the inverse fourth power of wavelength. This means that even a modest reduction in wavelength produces a large increase in scattering. Blue light is scattered several times more strongly than red light. As sunlight travels through the atmosphere, blue wavelengths are redirected in many directions. When someone looks away from the sun, some of that scattered blue light enters the eyes from almost every part of the sky. The sky is therefore not a blue surface suspended above Earth. It is sunlight being scattered by the atmosphere along countless paths. Violet light has an even shorter wavelength than blue light, so it is scattered more strongly. Yet the sky usually looks blue rather than violet. Several factors contribute. The sun emits less visible energy in the violet region than at nearby wavelengths. Some shorter wavelength radiation is absorbed in the upper atmosphere. Human eyes are also less sensitive to violet than to blue, and the overlapping responses of the cone photoreceptors influence the final perceived colour. The combination favours a blue appearance. The situation changes near sunrise and sunset. When the sun is high in the sky, its light passes through a relatively short atmospheric path before reaching the ground. Near the horizon, the light travels through a much longer section of atmosphere. Along this extended path, a greater proportion of the shorter blue and green wavelengths is scattered out of the direct beam. The light that remains travelling towards an observer becomes richer in yellow, orange, and red wavelengths. The sun itself may therefore appear orange or red, while parts of the surrounding sky glow with related colours. The exact appearance depends on atmospheric conditions. Dust, smoke, pollution, salt particles, and other aerosols can increase scattering and alter the distribution of colours. Aerosols are particles larger than individual gas molecules. When their sizes become comparable to visible wavelengths, the simple Rayleigh description is no longer sufficient. A broader framework called Mie scattering, developed from the work of the German physicist Gustav Mie, becomes important. Mie scattering is less strongly dependent on wavelength than Rayleigh scattering. It redirects a wider range of visible wavelengths more evenly, contributing to the white or grey appearance of clouds, haze and glare around the sun. Cloud droplets are much larger than visible wavelengths. They scatter red, green and blue light with broadly similar effectiveness. The mixture is perceived as white when the cloud is well illuminated. Thick clouds may appear grey because less light passes through them, and because repeated scattering spreads and weakens the illumination. Twilight produces several subtler atmospheric colours. After the sun has moved below the horizon, the upper atmosphere may still be illuminated while the ground lies in shadow. The sky can pass through yellow, orange, red, purple and deep blue as different paths and scattering conditions dominate. Opposite the setting sun, a dark blue-grey band may rise from the horizon. This is the shadow of Earth projected into the atmosphere. Above it can appear a pinkish band known as the Belt of Venus, created when reddened sunlight illuminates the atmosphere above Earth's shadow. The name is poetic, though the planet Venus is not responsible. It has enough to do already. Atmospheric water droplets produce another familiar display through refraction, internal reflection, and dispersion. A rainbow forms when sunlight enters an approximately spherical raindrop, bends as it crosses the surface, reflects inside the drop, and bends again as it leaves. Because the refractive index of water varies slightly with wavelength, different colours emerge at different angles. Red light leaves the drop at a slightly different angle from violet light. An observer sees a particular colour from each group of droplets depending on their position relative to the sun and the observer. A primary rainbow forms after one internal reflection. It usually appears with red on the outer edge and violet on the inner edge. The bright arc is centred on the point directly opposite the sun, which is why the sun must be behind the observer. A secondary rainbow forms when light undergoes two internal reflections inside the droplets. It appears outside the primary bow, is fainter, and has the colour order reversed, with violet towards the outer edge and red towards the inner edge. The region between the bows may appear darker because fewer rays emerge at the angles corresponding to that part of the sky. This area is called Alexander's dark band, named after Alexander of Aphrodisias, who described it in antiquity. Ice crystals high in the atmosphere produce different optical patterns. Halos often form when light is refracted through hexagonal ice crystals in cirrus clouds. A common halo appears roughly 22 degrees from the sun or moon. Sundogs are bright patches that can appear on either side of the sun. They form when sunlight passes through plate-shaped ice crystals oriented within the atmosphere. Their colours are usually subtle, with reddish tones nearest the sun. Refraction also changes the apparent position and shape of objects near the horizon. Earth's atmosphere becomes denser closer to the surface, so its refractive index changes gradually with altitude. Light from the sun or a star follows a slightly curved path through these layers. This bending makes celestial objects appear higher than their true geometric positions. The sun can remain visible briefly after it has physically passed below the horizon. Atmospheric refraction can also compress its vertical image, making it appear flattened near sunrise or sunset. Under unusual temperature conditions, changing refractive layers may distort distant objects, stretch them, duplicate them, or create mirages. These effects are not failures of vision. They are genuine changes in the paths taken by light. The atmosphere acts as a planetary optical laboratory. Gas molecules scatter blue light. Aerosols whiten the haze. Water droplets separate sunlight into rainbows. Ice crystals build halos, and layers of air bend the images of the sun and stars. The colours overhead are therefore not decoration added to the sky. They are visible evidence of electromagnetic radiation interacting with matter across the entire depth of Earth's atmosphere. The atmosphere redirects, filters and colours light, but seeing begins only when a small fraction of that light enters the eye. The eye does not send rays outward to touch objects. It receives light that has already been emitted, reflected or scattered by the world. Light first reaches the cornea, the clear curved surface at the front of the eye. The cornea provides most of the eye's refractive power, because light changes speed as it passes from air into the corneal tissue. Its shape bends incoming rays towards the retina. Behind the cornea lies the aqueous humour, a clear fluid filling the front portion of the eye. Light then passes through the pupil, the dark circular opening at the centre of the iris. The iris is the coloured ring of muscle surrounding the pupil. It changes the pupil's size in response to illumination. In bright conditions, the pupil narrows and reduces the amount of light entering. In dim conditions, it widens and allows more light through. The pupil is not a black object. It looks dark because most of the light entering it is absorbed inside the eye rather than returning directly to the observer. Behind the pupil sits the crystalline lens. The cornea performs most of the bending, while the lens fine-tunes the focus. Small muscles alter the lens's shape through a process called accommodation. When viewing a nearby object, the lens becomes more curved and increases its refractive power. When looking into the distance, it becomes flatter. This adjustment helps bring light from objects at different distances to a focus on the retina. After passing through the lens, light travels through the vitreous humor, a transparent gel filling most of the eyeball. It finally reaches the retina, a thin layer of neural tissue lining the back of the eye. The optical system produces an inverted image on the retina. Light from the upper part of a scene is focused on the lower retina, while light from the left side reaches the right side. The brain does not need to turn this image upright like someone rotating a photograph. Orientation is encoded through stable relationships between retinal positions, eye movements, touch, balance, and the wider organization of the nervous system. There is no tiny observer inside the head waiting for the picture to be corrected. The retina contains specialized light-sensitive cells called photoreceptors. The two principal types are rods and cones. Rods are extremely sensitive and support vision in low-light conditions. They are useful for detecting faint shapes and movement, but provide little color information. Cone photoreceptors operate best in brighter conditions and support detailed vision and color discrimination. The human retina contains roughly 120 million rods and around 6 million cones. Although the exact numbers vary between individuals, their distribution is uneven. Near the center of the retina is a small region called the fovea. It contains a very high density of cones and supports the sharpest vision. When someone looks directly at a word, a face, or a distant detail, eye movements place its image close to the fovea. Rods are largely absent from the central fovea and become more numerous farther from it. This is one reason faint stars can sometimes be seen more clearly by looking slightly to one side rather than directly at them. Their light then falls on a rod-rich region of the retina. There is also a location where the optic nerve leaves the eye. This region contains no rods or cones and is known as the blind spot. It does not normally appear as a visible hole because the brain uses surrounding information and input from the other eye to create a continuous scene. Photoreceptors do not merely behave like tiny buckets collecting light. They transform absorbed photons into changes in electrical signaling through a process called phototransduction. Inside these cells are light-sensitive pigment molecules. Each pigment contains a protein called an opsin, bound to a small light-sensitive molecule called retinal, which is derived from vitamin A. When retinal absorbs a photon, its molecular shape changes. This alters the attached opsin and begins a biochemical signaling cascade inside the photoreceptor. In darkness, photoreceptors maintain a steady flow of ions across their membranes and continuously release neurotransmitter. Light reduces that flow, causing the cell to become more electrically negative and change the amount of neurotransmitter it releases. This response is slightly counterintuitive. Light does not simply switch the photoreceptor on, in the everyday electrical sense. It changes an existing pattern of activity. Downstream retinal cells interpret those changes and begin separating information about contrast, edges, color, and motion. Rod photoreceptors contain the pigment rhodopsin, which is highly sensitive but takes time to recover after strong illumination. Moving from bright sunlight into a dark room therefore produces a period of poor vision. At first, cone sensitivity improves relatively quickly. Rods recover more slowly as rhodopsin is regenerated and retinal circuits adjust. Over roughly 20 to 30 minutes, rod-mediated sensitivity can increase enormously. This process is called dark adaptation. The changing size of the pupil contributes, but it accounts for only part of the improvement. Much of the increased sensitivity comes from chemical changes in photopigments and adjustments within the retina. Even a perfectly focused eye could not resolve unlimited detail. Light diffracts as it passes through the pupil, creating a fundamental diffraction limit. A very small pupil increases diffraction, while a very large pupil allows more optical imperfections to affect the image. The eye therefore operates through a compromise. In bright conditions, a smaller pupil can improve sharpness by reducing some aberrations, but if it becomes extremely small, diffraction begins to blur fine detail. In dim conditions, a larger pupil collects more light, but also allows more optical imperfections to contribute. The cornea and lens are not perfect optical components. Their curvature can produce spherical aberration, while different wavelengths may focus at slightly different positions through chromatic aberration. Irregularities in shape can cause astigmatism. The eye is often compared with a camera. The pupil resembles an aperture, the lens helps focus light, and the retina acts loosely like a sensor. The comparison is useful but incomplete. A camera usually records an image according to a fixed exposure and sensor arrangement. The eye is continuously moving, adapting, and changing focus. More importantly, the retina begins processing information before signals ever leave the eye. Photoreceptors connect to bipolar, horizontal, amacrine, and ganglion cells. These networks compare neighboring regions, enhance contrast, and organize visual signals. The output traveling along the optic nerve is not a simple untouched picture. Seeing is therefore not passive recording. Light supplies the physical input, but the eye selects, focuses, transforms, and processes that input from the moment photons reach the retina. What begins as electromagnetic radiation becomes a structured pattern of neural activity, ready to be interpreted as a visible world. The retina does far more than detect light. Before visual information has even left the eye, it has already been compared, filtered and organized into patterns that the brain can use. Photoreceptors respond when photons alter their light-sensitive molecules, but rods and cones do not send signals directly to the brain. Their activity passes through several layers of retinal cells. Bipolar cells receive signals from photoreceptors and help carry them towards retinal ganglion cells. Horizontal cells connect across neighboring regions, allowing the retina to compare light levels and enhance contrast. Amacrine cells contribute to timing, motion sensitivity, and more complex interactions within the retinal network. Retinal ganglion cells form the final output layer. Their long fibers gather together to create the optic nerve. Rather than reporting the brightness of every photoreceptor independently, many ganglion cells respond most strongly to differences between a central region and its surroundings. These center-surround receptive fields help emphasize edges and changes in brightness. A perfectly uniform patch of light produces less useful information than the boundary between light and dark. The retina therefore begins extracting structure before the signals travel any farther. The optic nerves carry this organized activity towards the brain. At the optic chiasm, fibers from the nasal half of each retina cross to the opposite side, while fibers from the temporal half remain on the same side. This arrangement sends information from the left side of the visual field to the right cerebral hemisphere, and information from the right side of the visual field to the left hemisphere. Each hemisphere receives input from both eyes, allowing the brain to compare their slightly different views. Many fibers continue to the lateral geniculate nucleus within the thalamus. The lateral geniculate nucleus is not simply a passive relay station. It preserves organized maps of the visual field and receives extensive feedback from the cerebral cortex, helping regulate which signals are emphasized. From there, much of the information travels to the primary visual cortex at the back of the brain. Neurons within this region respond to features such as edges, orientation, position, and movement. Visual processing then continues through multiple interconnected pathways involving areas specialized for form, color, motion, depth, and object recognition. There is no single point at which a complete internal picture suddenly appears. The visible world emerges from distributed activity across many regions working together. Colour begins with three main classes of cone photoreceptors. They have overlapping sensitivities to short, medium and long visible wavelengths. These are often described loosely as blue, green and red cones, but each class responds across a broad range rather than to one isolated colour. The British scientist Thomas Young proposed that human colour vision could arise from three types of receptor. The German physicist and physician Hermann von Helmholtz later developed the idea. Their account became known as the Young-Helmholtz theory of trichromatic colour vision. Colour is determined partly by comparing the relative activity of the three cone classes. A wavelength does not activate only one type of cone. Instead, it creates a pattern across all three. A second important framework was proposed by the German physiologist Ewald Hering. Opponent process theory describes colour information as being organised into opposing channels. Some neural pathways compare signals associated with red and green. Others compare blue and yellow. Another system compares light and dark. A response towards one side of an opponent channel tends to reduce or oppose the response associated with the other. Trichromatic theory and opponent process theory are not rivals describing completely separate systems. Trichromatic responses begin in the cone photoreceptors, while opponent comparisons emerge in retinal and later neural circuits. After images provide a simple demonstration, stare at a strongly coloured object for some time, then look at a pale surface. A complementary colour may briefly appear. Prolonged stimulation causes adaptation within particular receptors and opponent pathways, so the balance shifts when the original stimulus disappears. Adaptation also helps the visual system operate across enormous changes in illumination. A white sheet of paper may reflect vastly different amounts and combinations of light outdoors, beneath a warm lamp or under an overcast sky. Yet it usually continues to appear approximately white. This stability is called colour constancy. The brain estimates the likely colour of surfaces by considering surrounding objects, contrasts and the apparent illumination. It does not simply assign a colour from the raw wavelengths arriving at one small patch of retina. The process is useful but not infallible. Carefully designed visual illusions can make identical colours appear different when placed against different backgrounds. This is called simultaneous contrast. A grey square may appear lighter on a dark background and darker on a light one, even though its physical reflectance remains unchanged. Such effects show that perception depends on relationships. Brightness and colour are interpreted in context rather than measured as isolated values. Different physical spectra can also produce the same visual response. This phenomenon is called metamerism. Two light sources may contain very different mixtures of wavelengths, but activate the three cone classes in nearly identical proportions. A yellow patch on a display may be produced by combining red and green light, while a yellow flower reflects a broad and irregular range of wavelengths. If both create similar cone responses, they can appear to be the same colour. This principle allows screens to reproduce many colours using only three primary light sources. Red, green and blue light are combined through additive colour mixing. Adding all three at suitable intensities can produce the appearance of white. Paints and inks behave differently because they work mainly by absorption. Pigments remove selected wavelengths from the light falling upon them. Mixing pigments usually increases the range of wavelengths absorbed, producing subtractive colour mixing. Cyan, magenta and yellow are commonly used as subtractive primaries in printing, often with black added to improve depth and efficiency. Human colour vision also varies. Some people have altered or absent forms of one cone opsin, leading to common red-green colour vision deficiencies. Less common variations affect short wavelength discrimination, or produce greatly reduced colour perception. These differences are not simply a matter of seeing a normal world incorrectly. They represent genuine variations in the biological equipment through which the physical spectrum is sampled. Colour therefore does not exist entirely within light, objects or the brain alone. Illumination supplies a spectral distribution. Materials absorb and reflect wavelengths selectively. Photoreceptors respond through overlapping sensitivities, and neural circuits compare, adapt, and interpret those responses. The result is a stable and richly coloured world built from real physical signals, but shaped at every stage by the biology of seeing. Straight-line rays are excellent for tracing images through lenses and mirrors, but they cannot explain everything light does. When light passes through a narrow opening, moves around an edge, or overlaps with another beam, it reveals a distinctly wave-like character. One of the earliest useful ways to describe this behaviour came from the Dutch physicist Christian Huygens. His wavefront principle states that every point on a wavefront can be treated as a source of smaller secondary wavelets. As these wavelets spread, their combined envelope forms the next wavefront. This picture helps explain why a broad wave continues forwards through open space, but also why light can spread after passing through an aperture. The smaller the opening becomes compared with the wavelength, the more noticeable that spreading can be. The wave nature of light became especially clear through the work of the English scientist Thomas Young. In the early 19th century, Young directed light through two closely spaced openings. Instead of producing only two bright regions behind them, the light formed a sequence of bright and dark bands known as interference fringes. Each opening acted as a source of spreading waves. Where the two waves arrived in step, their electric fields reinforced one another. This is constructive interference, and it produced a bright fringe. Where the waves arrived sufficiently out of step, one oscillation opposed the other, their fields partially or completely cancelled. This is destructive interference, producing a dark fringe. The important factor is phase, meaning the position within the repeating wave cycle. Two waves in phase rise and fall together. Waves separated by half a cycle oppose one another most strongly. Interference does not mean that light energy has vanished permanently from the dark regions. The overlapping waves redistribute where energy is detected, increasing intensity in some places while reducing it in others. Diffraction is closely related. It describes the spreading and reshaping of waves when they pass through openings, travel around obstacles, or encounter structures. The effect exists at all scales, but it becomes most obvious when the size of the obstacle or aperture is comparable to the wavelength. Visible wavelengths are only a few hundred nanometers long, so diffraction around everyday objects is usually subtle. Sound wavelengths are much longer, which is why voices can be heard around corners more easily than a lamp can be seen through them. When light passes through a circular aperture, it does not form a perfectly sharp point on a screen. Even an ideal lens produces a central bright disk surrounded by faint rings. This pattern is called the Airy pattern, named after the British astronomer and mathematician George Biddle Airy. The existence of the Airy pattern creates a diffraction limit. Two nearby point sources produce overlapping patterns, and if they are too close together, they cannot be distinguished clearly. This limits the resolving power of telescopes, microscopes, cameras, and the human eye. A larger telescope aperture produces a narrower diffraction pattern and can distinguish finer angular detail. A microscope can improve resolution by using shorter wavelengths and a suitable optical arrangement, but no ordinary lens can reveal infinitely small features. The French physicist Augustin Jean Fresnel developed a detailed mathematical theory of diffraction and interference. His work provided increasingly precise predictions for how light should behave around obstacles and through openings. One famous episode involved Simeon Denis Poisson, who examined Fresnel's theory while serving on a scientific committee. Poisson pointed out that the equations predicted a bright spot at the centre of the shadow, behind a small circular object. He considered this prediction absurd and believed it weakened the wave theory. The physicist François Arago performed the experiment and found the bright point exactly where the theory predicted. It became known as the Poisson spot, or sometimes the Arago spot. An objection intended to defeat the wave model instead became one of its most memorable confirmations. Physics can occasionally display a rather dry sense of humour. Another behaviour that strongly supports the wave description is polarization. In an electromagnetic wave, the electric field oscillates perpendicular to the direction of travel. Polarization describes the organisation of that oscillation. In linearly polarised light, the electric field oscillates along a fixed direction. In circularly polarised light, the direction of the electric field rotates steadily while its magnitude remains constant. Elliptically polarised light is the more general case, where the tip of the electric field vector traces an ellipse. Ordinary sunlight and most lamps produce largely unpolarised light, containing many rapidly changing orientations. A polarizing filter selects one component, transmitting electric field oscillations aligned with its transmission direction and reducing others. Malus's law, named after the French physicist Étienne Louis Malus, describes how the intensity changes when linearly polarized light passes through a second polarizer. The transmitted intensity equals the original intensity multiplied by the square of the cosine of the angle between the light's polarization direction and the filter's transmission direction. When the directions align, transmission is strongest. When they are perpendicular, an ideal second polarizer blocks the light. Polarizing sunglasses reduce glare because light reflected from surfaces such as water or roads often becomes partially polarized. The filters are oriented to suppress much of that reflected component. Liquid crystal displays also rely on polarization. Electric fields change the orientation of liquid crystal molecules, altering how they affect polarized light passing through the display. Combined with filters and colored subpixels, this controls the brightness and color of each visible region. Polarization can reveal stresses within transparent materials because internal strain changes how different polarization components travel. Engineers use this effect in photoelastic stress analysis. Some insects and other animals can detect patterns of polarized skylight and use them for navigation. Astronomers study polarization to investigate magnetic fields, dust, scattering environments, and the physical conditions around distant objects. Interference also creates the shifting colours of soap bubbles and thin oil films. Light reflects from both the front and rear boundaries of the thin layer. The two reflected waves travel slightly different distances and may also undergo phase changes at the boundaries. Depending on the layer thickness, viewing angle and wavelength, some colours reinforce while others cancel. As a soap film changes thickness, the pattern of colours flows across its surface. Anti-reflective coatings use the same principle deliberately. A thin layer is designed so that reflected waves cancel across a selected wavelength range, allowing more light to pass through a lens or screen. Interference, diffraction, and polarization cannot be explained completely by treating light as nothing more than straight rays or miniature classical projectiles. They reveal propagation governed by phase, wavelength, and oscillating electromagnetic fields. Yet the wave picture is not the entire story either. Light forms smooth interference patterns, but it is emitted and detected through discrete exchanges of energy. The same phenomenon that spreads through space like a wave can arrive at matter in individual quantum events. By the end of the 19th century, the wave theory of light had become extraordinarily successful. Interference, diffraction, and polarization all showed that light behaved in ways that ordinary particles could not easily reproduce. James Clerk Maxwell had also united light with electricity and magnetism, describing it as an electromagnetic wave. Yet one stubborn problem remained. Physicists were trying to understand the radiation emitted by hot objects. A heated material produces a broad range of electromagnetic wavelengths, and the shape of that distribution changes with temperature. The idealized version of such an emitter is called a blackbody, meaning an object that absorbs incoming radiation perfectly and emits a spectrum determined only by its temperature. Classical physics could describe parts of the spectrum reasonably well. At longer wavelengths, its predictions matched observations. At shorter wavelengths, however, the theory failed dramatically. The classical calculation suggested that a hot object should emit more and more energy as the wavelength became shorter. Taken literally, the predicted energy would rise without limit in the ultraviolet region and beyond. This failure became known as the ultraviolet catastrophe. The name sounds as though laboratories were being flooded with infinite ultraviolet light, which would have made 19th century physics conferences rather difficult to attend. In reality, no such catastrophe occurred in nature. Hot objects did not emit infinite energy. The catastrophe belonged to the theory, not to the physical world. In 1900, the German physicist Max Planck found a mathematical way to reproduce the observed blackbody spectrum. He proposed that matter could emit and absorb electromagnetic energy only in discrete amounts. These individual quantities were called quanta. Planck found that the size of each quantum depended on the frequency of the radiation. The energy of a quantum equals Planck's constant multiplied by its frequency. Planck's constant is an extremely small fundamental quantity. Its smallness helps explain why energy often appears continuous in everyday life. At microscopic scales, however, the discreteness becomes impossible to ignore. Higher frequency radiation is exchanged in larger energy packets. Lower frequency radiation is exchanged in smaller ones. This restriction prevented the unlimited buildup of energy predicted by classical theory at very high frequencies. Planck initially approached quantization cautiously. He had discovered a rule that worked, but he did not immediately insist that electromagnetic radiation itself consisted of literal particles. The idea was introduced as a property of the way matter exchanged energy. Its consequences soon became much larger. Another puzzle involved the photoelectric effect. When light strikes certain metal surfaces, electrons can be released. Classical wave theory suggested that the energy carried by light should depend mainly on its intensity. A brighter beam should deliver energy more quickly, so sufficiently intense light of any frequency might be expected to eject electrons after enough time. Experiments showed something different. Below a particular threshold frequency, no electrons were released, however intense the light became. Increasing the brightness of low-frequency light did not solve the problem. Above the threshold frequency, electrons could be emitted almost immediately even when the light was faint. The maximum kinetic energy of the released electrons depended on the frequency of the light, not simply on its intensity. In 1905, Albert Einstein proposed a bold explanation. He suggested that light itself behaves as though its energy is concentrated into localized quanta. These light quanta were later called photons. Each photon carries an amount of energy determined by its frequency. One photon transfers its energy through an individual interaction. If that energy is below the amount required to free an electron from the material, the electron remains bound. Sending more low-energy photons increases the total energy arriving at the surface, but each photon is still individually insufficient. It is rather like sending a large number of envelopes, each containing too little money to pay a fixed entrance fee. The quantity of envelopes does not change the amount inside each one. Once the photon frequency rises above the threshold, an individual photon can provide enough energy to release an electron. Part of the photon's energy is used to overcome the binding energy of the material, often described by the work function. Any remaining energy appears mainly as kinetic energy of the emitted electron. Increasing the intensity above the threshold generally means sending more photons each second. More photons can therefore release more electrons, provided suitable electrons and interactions are available. Increasing the frequency raises the energy carried by each photon and can increase the energy of the emitted electrons. Einstein's explanation treated the exchange of light and matter as fundamentally discrete. It was one of the major steps in the development of quantum physics. His work on the photoelectric effect was specifically recognized when he received the Nobel Prize in Physics. The award was not given for special relativity or general relativity, despite those theories later becoming his most famous achievements. The photon idea did not make the evidence for waves disappear. Light still produced interference and diffraction. The new problem was that it also transferred energy in individual localized events. Further evidence came from the American physicist Arthur Compton. In the early 1920s, Compton studied the scattering of X-rays from electrons. If X-rays were treated only as classical waves, the observed change in wavelength was difficult to explain. Compton found that the results could be described as collisions between photons and electrons. A photon entered with a particular energy and momentum. After interacting with an electron, the photon emerged in a different direction, with a longer wavelength and therefore lower energy. The electron carried away the missing energy and momentum. This became known as the Compton effect. The results showed that photons possess momentum, even though they have no rest mass. For a photon, momentum is connected to wavelength. The momentum of a photon equals Planck's constant divided by its wavelength. Shorter wavelength photons carry more momentum than longer wavelength photons. When light is absorbed, reflected or scattered, it can transfer part or all of that momentum to matter. This produces radiation pressure. The force from ordinary light is usually extremely small, but it can be measured. Sunlight exerts pressure on planets, dust particles and spacecraft. Solar sails are designed to use this steady transfer of momentum for propulsion. On microscopic scales, tightly focused laser beams can exert enough force to trap and move tiny particles. This technique is known as optical trapping or optical tweezers and was developed extensively by the physicist Arthur Ashkin. Care is needed when using familiar demonstrations of light pressure. The Crookes radiometer, with its dark and pale vanes rotating inside a partially evacuated glass bulb, is often presented as a direct photon-powered device. Its motion, however, is dominated by thermal interactions with the remaining gas rather than simple radiation pressure alone. Genuine radiation pressure is real. The radiometer is simply a slightly more complicated character than its reputation suggests. The quantum revolution did not overturn the wave behavior of light. It revealed that the classical wave description was incomplete. Light propagates in ways that display interference, phase and diffraction, yet it exchanges energy and momentum through discrete quantum events. Nature had not chosen between waves and particles in the familiar classical sense. It had introduced a deeper framework in which light could display features of both, while being fully identical to neither. The double-slit experiment becomes even stranger when the light source is weakened until photons pass through the apparatus one at a time. Each photon eventually produces a single localized detection. It may leave a tiny mark on a photographic plate or trigger one small region of an electronic detector. Nothing appears as a faint wave spread continuously across the entire screen. Each recorded event occurs at one particular location. At first, the detection seems random. One photon arrives here, another appears somewhere else, and no obvious structure is visible. Yet as hundreds, thousands and eventually many more photons accumulate, a familiar pattern emerges. Bright bands form where detections are common. Dark bands appear where detections are rare or effectively absent. The full distribution matches the interference pattern expected from waves passing through both slits. This happens even when the photons are separated by enough time that only one is travelling through the apparatus at once. The pattern is not being created by ordinary collisions between different photons. Each individual photon contributes to a distribution governed by interference. It is tempting to imagine that the photon secretly divides into two smaller classical pieces, sends one fragment through each slit, and then rejoins itself before reaching the detector. That picture does not work. A photon is detected as a complete quantum event, and experiments do not reveal two half-photons travelling along separate ordinary paths. Quantum theory describes the situation using a quantum state. This state does not function like a simple map showing one definite but unknown route. Instead, it assigns probability amplitude to the possible alternatives, including propagation through each slit and detection at different positions. A probability amplitude is not itself an ordinary probability. It carries information about both magnitude and phase. Amplitudes associated with different alternatives can be added together before probabilities are calculated. Where the amplitudes reinforce one another, detection becomes more likely. Where they oppose one another, detection becomes less likely. In some regions, the amplitudes can cancel almost completely, producing the dark fringes of the interference pattern. The German physicist Max Born introduced the rule connecting these amplitudes to measurable probabilities. The Born rule states that the squared magnitude of a quantum amplitude determines the probability of obtaining a particular outcome. The theory therefore predicts the distribution of many detections with great accuracy, even though it does not generally specify the exact position at which one individual photon will appear. This combination of precise statistics and unpredictable individual outcomes is one of the defining features of quantum physics. The theory is not vague about the pattern, it is simply probabilistic about each event within it. The interference disappears when the apparatus is modified to reveal which slit the photon passes through. A detector may be placed near the openings, or the photon may become correlated with some distinguishable marker associated with one path. Once reliable which path information exists, the smooth interference fringes are replaced by a distribution resembling the sum of two separate single-slit patterns. This does not require a conscious observer to look at the result. Quantum measurement is a physical interaction. The photon becomes correlated with a detector, a marker, or some part of the surrounding environment. The two alternatives can then be distinguished in principle. The loss of interference is connected to decoherence. Decoherence occurs when different parts of a quantum state become entangled with many uncontrolled degrees of freedom in the environment. A photon taking one alternative may leave the detector or surroundings in one physical state, while the other alternative leaves them in another. If those environmental states become effectively distinguishable, the phase relationship required for observable interference is dispersed into a much larger system. The alternatives have not necessarily been disturbed by a crude mechanical shove. What matters is that information about the path has become physically available. A related arrangement is the matched Zander interferometer. A beam splitter provides two alternative optical paths. Mirrors redirect those paths, and a second beam splitter brings them together again. When the path lengths and phases are arranged appropriately, the probability amplitudes interfere. One output detector may receive nearly all the photons, while the other receives almost none. Each photon is still detected at one output, but the final probabilities depend on both possible paths through the device. If a witch path detector is added, the interference changes or disappears. The experiment demonstrates that quantum alternatives influence outcomes even when no classical object can be assigned an ordinary route through the apparatus. The physicist Niels Bohr described related situations using the principle of complementarity. Some experimental arrangements reveal interference and other wave-like properties. Others reveal path information and localize particle-like detections. The complete behavior cannot be represented by combining incompatible classical pictures into one ordinary mechanical story. This does not mean that a photon physically changes from a tiny wave into a tiny pellet whenever the laboratory equipment is adjusted. Modern quantum theory describes one quantum system whose possible outcomes depend on the physical interaction used to examine it. Delayed choice experiments, associated especially with the American physicist John Archibald Wheeler, make this point particularly vivid. In one form, the decision to preserve or destroy interference is made only after the photon has entered the apparatus. Popular descriptions sometimes claim that the later choice reaches backwards through time and changes what the photon already did. That conclusion assumes the photon must have possessed a definite classical history before the measurement arrangement was completed. Quantum theory does not require such a history. It assigns amplitudes to the complete experimental alternatives and predicts correlations between the preparation, the apparatus, and the final detection. The later choice changes which physical distinctions can appear in the results. It does not need to rewrite an already settled classical past. Wave-particle duality remains useful as a historical phrase. It reminds us that light produces interference like a wave and arrives in localized exchanges like a particle. Yet the phrase can also mislead if it suggests that light repeatedly switches between two familiar identities. A photon is not secretly a water wave on some occasions, and a microscopic marble on others. It is a quantum excitation described by amplitudes, phases, and probabilities. Its behavior includes wave-like propagation and particle-like detection, because both are limited classical glimpses of a deeper structure. One photon can therefore contribute to a pattern shaped by two possible paths. It arrives only once, at one location, yet the probability of that arrival reflects alternatives that cannot be reduced to a single ordinary trajectory. The word photon is useful, but it can easily create the wrong picture. It may suggest a tiny glowing sphere travelling through space with a sharp boundary, a fixed path, and perhaps a faintly determined expression. That is not how modern physics describes it. In quantum field theory, the electromagnetic field is treated as a fundamental field extending throughout space. A photon is a quantized excitation of that field. This means that the photon is not a separate little object placed inside the electromagnetic field. It is a particular way in which the field can carry energy, momentum, and polarization. The amount of energy associated with a photon depends on its frequency. The energy of a photon equals Planck's constant multiplied by its frequency. Its momentum is related to its wavelength. The momentum of a photon equals Planck's constant divided by its wavelength. These relationships explain why higher frequency photons carry more energy and why shorter wavelength photons carry more momentum. A photon has no rest mass. It cannot be brought to rest and examined like an ordinary material particle. When freely propagating through vacuum, it travels at the speed of light. It also does not possess a definite outer surface. There is no small shell marking where the photon ends and empty space begins. Depending on the quantum state, the probability of detecting it may be spread across a large region or concentrated into a relatively narrow wave packet. This does not mean that a fraction of a photon is physically smeared everywhere in the same way that a thin mist is spread through a room. When the photon is absorbed by a detector, the exchange occurs as a complete quantum event. The spread belongs to the quantum state and its possible outcomes. The theory describing electromagnetic interactions at this level is called quantum electrodynamics. It combines quantum mechanics, special relativity, and the electromagnetic field into a highly successful framework. Quantum electrodynamics describes how charged particles such as electrons and positrons interact through the electromagnetic field. It includes the emission, absorption, and scattering of photons, along with more complicated processes that contribute to measurable probabilities. Major formulations of the theory were developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. Their work was recognized with the Nobel Prize in Physics in 1965. Quantum electrodynamics is famous for the precision of its predictions. Calculations involving the magnetic properties of the electron agree with experiments to extraordinary accuracy. This does not mean every calculation is simple, quite the opposite. The theory is exceptionally successful and occasionally rather determined to make physicists earn their coffee. One of the best-known tools associated with the theory is the Feynman diagram. These diagrams use lines and vertices to organize mathematical contributions to an interaction. An electron may be represented by one kind of line, a photon by another, and a point where they interact by a vertex. A diagram can make a complicated calculation easier to visualize and organize. However, a Feynman diagram is not a literal film of tiny objects moving through space along visible tracks. The internal lines do not necessarily represent directly observable particles following definite trajectories. They are components of a mathematical expansion used to calculate probability amplitudes. This distinction becomes especially important when discussing virtual photons. A real photon can propagate freely and be detected as radiation. It can leave a source, cross a laboratory, and deposit energy in a detector. A virtual photon appears within certain perturbative calculations. It is not an ordinary freely travelling photon that could be intercepted and measured in the same way. Its energy and momentum need not satisfy the same relationship as those of a real photon. It is common to hear that electric and magnetic forces occur because charged particles exchange virtual photons. This can be a useful shorthand within a particular calculational framework, but it should not be imagined as a stream of detectable light particles constantly flying between stationary charges. The underlying description is the interaction of charged quantum fields with the electromagnetic field. Virtual particles are features of one way of organizing the mathematics, not hidden projectiles waiting to be photographed. Photons also possess an intrinsic quantum property called spin. They are described as spin-1 particles, although quantum spin is not the same as a small object physically rotating around an axis. For a freely propagating photon in vacuum, the measurable spin information is expressed through helicity. Helicity describes the relationship between the photon's angular momentum and its direction of motion. A photon can have either of two physical helicity states. These are closely connected with the two possible circular polarizations of light. Linear polarization can be described as a quantum superposition of these helicity states. Photons belong to a class of particles called bosons. Bosons can occupy the same quantum state in large numbers. They do not obey the exclusion principle that prevents identical fermions such as electrons from all sharing one state. This bosonic behavior helps make lasers possible. In an idealized coherent laser field, many photons occupy closely related modes with organized phase relationships. The result can be highly directional, narrow in frequency, and extremely intense. Photon number is not always conserved. Photons can be created when atoms change energy states, when charged particles accelerate, or when other particles interact. They can also be destroyed through absorption, or converted into other particles when sufficient energy and the correct conditions are available. This does not violate conservation laws. Total energy, momentum and angular momentum remain conserved. Electric charge is also conserved, and the photon itself carries no electric charge. Quantum field theory also assigns a lowest energy state to the electromagnetic field, called the vacuum state. This vacuum is not simply a classical absence of all activity. Quantum observables can still possess irreducible fluctuations. Vacuum fluctuations have measurable consequences in suitable physical arrangements. However, the popular image of fully formed particles constantly popping into existence, borrowing energy, and vanishing again is usually too literal. The vacuum is a quantum state of fields. Its fluctuations describe the structure and uncertainty of that state, not necessarily a hidden swarm of ordinary particles briefly ignoring the rules. Classical electromagnetic waves emerge when many photons occupy suitable quantum states. A particularly important example is the coherent state, which closely reproduces the behavior of a classical oscillating field. A bright radio signal or laser beam can therefore be described very effectively through classical fields, even though its emission and detection ultimately involve quantum processes. The classical wave is not wrong. It is an extremely accurate large-scale description, under conditions where individual quantum events are not the main focus. The different pictures of light now fit together more clearly. A ray describes the direction of propagation, when wavelength effects can be neglected. A classical electromagnetic wave describes changing electric and magnetic fields. A photon describes a quantum excitation involved in discrete interactions. Quantum electrodynamics provides the deeper framework connecting light with charged matter. These are not competing identities between which light must choose. They are related descriptions suited to different questions and scales. A photon is therefore neither a conventional wave nor a conventional particle. It is a quantum excitation of the electromagnetic field, carrying definite units of energy, momentum and angular momentum while being described through amplitudes and probabilities. The mystery of light does not disappear under this description, but it becomes more precise. What once seemed like a contradiction between waves and particles becomes a sign that both classical pictures were partial views of a field governed by quantum laws. Light travels through empty space at approximately 299,792 kilometers per second. Inside water, glass, and many other transparent materials, its measured propagation is slower. That familiar statement is correct, but it compresses several different ideas into one sentence. To understand what is really happening, it helps to separate phase velocity, group velocity, and the speed at which new information can travel. An electromagnetic wave contains oscillating electric and magnetic fields. When the wave enters matter, its electric field acts upon the charged particles within the material, especially electrons. Those charges respond by moving slightly away from their equilibrium positions, and then being pulled back by the forces binding them to atoms or molecules. The moving charges generate electromagnetic fields of their own. The original field and the material's response combine, producing a new pattern of propagation through the substance. The light is therefore not simply travelling through empty gaps while occasionally bumping into atoms. It is participating in a collective electromagnetic interaction with the material. This behaviour is summarised by the refractive index. For a simple transparent medium, the refractive index compares the speed of light in vacuum with the phase velocity of light inside the material. The refractive index equals the speed of light in vacuum divided by the phase velocity in the material. Ordinary window glass has a visible light refractive index of roughly 1.5. This means that the phase of a visible electromagnetic wave moves through the glass at about 2/3 of the vacuum speed of light. Water has a refractive index of approximately 1.33 for visible light, so the corresponding phase velocity is about 3/4 of the vacuum speed. The phrase phase velocity refers to the speed at which a particular point in a repeating wave pattern moves, such as a crest or a fixed phase of the oscillation. A perfectly continuous sinusoidal wave does not carry a beginning, an ending, or a message by itself. so its phase velocity is not always the same thing as the speed of information. Real signals are usually pulses or changing patterns made from many nearby frequencies. The envelope of such a pulse often moves at the group velocity. In many ordinary transparent materials, the group velocity is closely related to the speed at which energy and information are transported, although extreme or strongly dispersive conditions require more careful language. The familiar explanation that photons are repeatedly absorbed and re-emitted by individual atoms is usually too crude for transparent materials. If a photon were truly absorbed into a long-lived atomic state and later emitted independently, the new photon would generally lose the precise phase and directional relationship required to preserve a clear image. Random absorption and spontaneous re-emission would tend to scatter the light rather than transmit it neatly through a window. Ordinary transparent propagation is better described through the coherent response of the material. The incoming electromagnetic field drives many charged particles. Their emitted fields remain phase-related to the original wave and combine with it. Most of the secondary radiation cancels in directions away from the forward path. In the forward direction, it combines coherently with the incoming field and alters the phase of the resulting wave. This process is often described as coherent forward scattering. The overall effect is a wave that propagates through the material with a modified phase velocity and wavelength, while its frequency remains fixed at a stationary boundary. The material's response depends on frequency. Bound electrons, molecular vibrations, and molecular rotations each have natural resonant frequencies. Near one of these resonances, the charges respond especially strongly to the incoming field. Electronic resonances commonly occur in the visible or ultraviolet range. Molecular vibrations often interact strongly with infrared radiation, while molecular rotations can interact with microwave frequencies. If the frequency lies far enough from a strong resonance, a material may transmit the light with relatively little absorption. Closer to a resonance, energy transfer into the material becomes more effective, and absorption can rise sharply. This explains why a substance may be transparent to one part of the electromagnetic spectrum and opaque to another. Glass transmits much of visible light, but absorbs important parts of the ultraviolet and infrared. Water is relatively transparent across a portion of the visible spectrum, yet absorbs strongly across many infrared and microwave wavelengths. The refractive index also varies with wavelength. This is called dispersion. In normal dispersion, shorter visible wavelengths usually experience a slightly higher refractive index than longer wavelengths. Violet light therefore travels with a lower phase velocity in glass than red light, and bends more strongly at a boundary. This is why prisms separate white light into a spectrum and why simple lenses can produce chromatic aberration. Group velocity depends on how the refractive index changes across the frequencies making up a pulse. Different frequency components accumulate phase at different rates, so a pulse may broaden, change shape, or travel at a speed distinct from the phase velocity. Near strong resonances, the dependence can become unusual. In anomalous dispersion, the refractive index may decrease with increasing frequency across a particular range. Under carefully prepared conditions, calculated group velocities can become greater than the vacuum speed of light, extremely large or even negative. These results do not allow a message to outrun light in vacuum. The peak of a pulse is not always a permanent object moving intact through the material. Strong dispersion can reshape the pulse by attenuating some frequency components and advancing others. A later peak may be constructed from the early leading portion of the incoming signal. The arrival of genuinely new information is associated with the leading causal disturbance, sometimes called the signal front. That front cannot propagate faster than the vacuum speed of light. Relativistic causality remains intact, however eccentric the pulse peak may appear. Physicists have also created slow light systems in which the group velocity becomes dramatically reduced. Techniques involving ultra-cold atomic gases, coherent interactions, and carefully controlled resonances have slowed optical pulses to walking speed and, in specialized experiments, effectively stored their quantum state within matter before releasing it again. This does not mean that the fundamental speed of a light has been altered. The vacuum constant remains unchanged. The delay arises from the way the pulse interacts with the material and shares its excitation with the atomic system. A striking related effect occurs when a charged particle travels through a material faster than light's local phase velocity in that medium. The particle is still moving more slowly than light travels in vacuum, so relativity is not violated. It merely outruns the electromagnetic disturbance, as that disturbance propagates through the material. This produces Cherenkov radiation, named after the Soviet physicist Pavel Cherenkov, who studied the effect experimentally during the 1930s. As a fast-charged particle passes through a transparent material, it polarizes nearby atoms and molecules. Their electromagnetic responses combine coherently along a cone, somewhat like the shock wave produced when an aircraft exceeds the speed of sound in air. The comparison is useful, although Cherenkov radiation is an electromagnetic phenomenon rather than an ordinary pressure wave. The vivid blue glow seen in the water surrounding some nuclear reactors is produced largely by this process. Energetic electrons released by nuclear reactions can move through the water faster than light's phase velocity there. Their passage generates a cone of Cherenkov radiation. The glow appears blue partly because the emitted intensity is stronger at shorter visible wavelengths, although material absorption, detector sensitivity, and the human visual system also influence the observed colour. Light does not truly slow down because photons become tired, queue politely behind atoms, or spend most of their journey parked in excited states. Its propagation through matter is a collective process involving the electromagnetic field and the charge structure of the material. Phase, pulse energy, and information can behave differently under specialized conditions, but the central limit remains firm. No causal signal outruns light in vacuum. The speed of light through matter is therefore not a modification of the universe's ultimate speed limit. It is a visible consequence of the intricate way electromagnetic fields and material particles respond to one another. Once the behavior of light was understood well enough, people could begin controlling it with remarkable precision. Mirrors, lenses, semiconductors, lasers, and optical fibers all manipulate the same basic properties: wavelength, direction, phase, energy, and interaction with matter. Some of the earliest powerful optical technologies relied on shaped glass and curved mirrors. A lens redirects light through refraction, while a curved mirror redirects it through reflection. By arranging these surfaces carefully, an optical system can form magnified or distant images. Microscopes use lenses to collect light from very small structures and enlarge their apparent detail. Early compound microscopes opened a world of cells, microorganisms, and fine biological structures that human eyes could not resolve unaided. Telescopes perform a related task at a vastly different scale. Refracting telescopes use lenses, while reflecting telescopes use curved mirrors. Both gather more light than the human eye and bring distant objects into sharper view. The amount of light collected depends strongly on the size of the aperture. Larger telescopes can observe fainter objects and, within limits set by diffraction and atmospheric turbulence, resolve finer details. Carefully controlled light therefore extends human vision from microscopic cells to galaxies millions or billions of light-years away. Photography offered another way to capture light. Traditional photographic film contains light-sensitive chemical compounds, often based on silver halides. Incoming photons trigger chemical changes within microscopic grains. Later processing amplifies and stabilizes those changes, creating a lasting image. Digital cameras replace chemical film with semiconductor sensors. Two major forms are charge-coupled devices and complementary metal oxide semiconductor sensors. When photons strike a suitable semiconductor, their energy can release mobile charge carriers through the photoelectric effect. Each sensor element collects electrical charge roughly in proportion to the amount of light received. Electronic circuits then measure these charges and convert them into numerical image data. Color cameras usually place filters over different sensor elements so that separate regions respond mainly to red, green, or blue light. Software combines these measurements into a full-color image. Semiconductors can also produce light. In a light-emitting diode, electrons and electron vacancies, commonly called holes, are brought together across a junction between semiconductor regions. When they recombine, energy may be released as a photon. The photon energy is linked to the semiconductor band gap, which is the energy difference between allowed electronic states. A larger band gap generally produces higher frequency, shorter wavelength light. Different materials and structures therefore produce infrared, red, green, blue, or ultraviolet emission. White light-emitting diodes often use a blue or ultraviolet diode, combined with phosphor materials that absorb some photons and re-emit light across longer wavelengths. The mixture is perceived as white. Lasers provide even tighter control. Their operation depends on stimulated emission, in which one photon encourages an excited atom, molecule, or semiconductor system to emit another photon with matching properties. The development of the laser grew from earlier work on the maser, which amplified microwave radiation. Charles Townes helped develop the first maser, while Nikolai Basov and Alexander Prokhorov independently developed important theoretical ideas for amplified electromagnetic emission. Charles Townes and Arthur Schawlow later described principles for extending this process to visible and infrared light. In 1960, Theodore Maiman built the first working laser using a synthetic ruby crystal. Laser light is often highly directional, so it spreads far less than light from an ordinary lamp. It can also have a narrow spectral width, meaning that much of its energy lies within a small frequency range. Another important property is coherence. The electromagnetic oscillations maintain well-organized phase relationships over useful distances and times. Perfect coherence is an idealization, but real lasers can achieve much greater coherence than most thermal sources. These properties make lasers suitable for scanning barcodes, reading optical discs, performing precise surgery, cutting materials, and measuring distance. Compact discs, digital versatile discs, and Blu-ray discs store information as microscopic patterns along spiral tracks. Lasers with different wavelengths can focus to different spot sizes, allowing shorter wavelength Blu-ray systems to store data more densely. Interferometers divide and recombine light to measure tiny differences in distance or refractive index. Because interference depends sensitively on phase, even extremely small changes in path length can shift the resulting pattern. In manufacturing, focused lasers can cut, weld, engrave, and modify surfaces with great precision. In medicine, selected wavelengths can reshape the cornea, seal blood vessels, or target particular tissues while limiting damage to surrounding regions. Arthur Ashkin demonstrated that light can also move matter directly. In optical tweezers, a strongly focused laser beam creates forces that can trap microscopic particles near the region of highest intensity. The technique can hold tiny dielectric spheres, cells, and biological molecules without ordinary mechanical contact. Arthur Ashkin's work on optical tweezers was recognized with the Nobel Prize in Physics. Light is equally important for communication. Optical fibers guide electromagnetic waves through thin strands of extremely pure glass or plastic. The central core has a slightly higher refractive index than the surrounding cladding, allowing light to remain confined through guided propagation closely related to total internal reflection. Modern fibers lose only a small fraction of their light over many kilometers. Repeaters or optical amplifiers can restore signals across longer routes. Wavelength division multiplexing allows several optical signals with different wavelengths to travel through the same fiber simultaneously. Each wavelength acts as a separate communication channel, greatly increasing the amount of information that can be transmitted. Much of the global internet travels as pulses of light through fiber networks beneath streets, across countries, and along cables resting on the ocean floor. A message may feel almost immaterial, yet it often spends part of its journey as carefully modulated infrared light inside glass. Light detection and ranging, commonly called LIDAR, uses timed laser pulses to measure distance. A pulse is emitted, reflected by a surface, and detected on its return. Distance equals the speed of light multiplied by the round-trip travel time divided by 2. The division by 2 accounts for the outward and return journeys. Repeating this measurement across many directions can produce detailed three-dimensional maps. LIDAR is used in surveying, archaeology, atmospheric research, spacecraft navigation, and some autonomous systems. It can reveal ground features beneath forest canopies, measure cloud layers, or map the shape of a distant asteroid. Solar cells reverse part of the process used by light-emitting diodes. Incoming photons transfer energy to electrons in a semiconductor. If the photon energy is sufficient, charge carriers can be separated by an internal electric field and driven through an external circuit. A solar cell does not store sunlight inside itself. It converts part of the arriving electromagnetic energy into electrical energy. Batteries may later store that electrical energy through chemical changes, but the photovoltaic device performs the initial conversion. Modern technology controls light at every stage. Lamps and diodes create it. Mirrors, lenses, and fibers direct it. Filters and interferometers shape its wavelength and phase. Cameras detect it. Solar cells convert its energy, and optical tweezers use its momentum. The principles behind these devices are the same ones visible in prisms, shadows, soap bubbles, and stars. Human control of light did not require inventing new behavior. It came from learning how to guide the behavior that nature had been displaying all along. Almost everything known about the distant universe has arrived as light. Astronomers cannot travel to stars, collect samples from most planets, or place instruments inside remote galaxies. Instead, they study electromagnetic radiation that has crossed space, carrying information about the places where it began and the matter it encountered along the way. Light is therefore not merely something that makes the universe visible. It is the universe's most widely available messenger. Because light has a finite speed, every astronomical observation is also a view into the past. Sunlight takes a little more than 8 minutes to reach Earth. The sun seen in the sky is therefore the sun as it was roughly 8 minutes earlier. Light from Proxima Centauri, the nearest star beyond the sun, travels for more than 4 years before arriving. The Andromeda Galaxy is seen as it existed roughly 2.5 million years ago. More distant galaxies may appear as they were billions of years in the past, when the universe was far younger. The night sky is not a single present moment. It is a layered record assembled from signals with different travel times. One of the most powerful ways to read those signals is astronomical spectroscopy. A spectroscope separates incoming radiation according to wavelength, revealing patterns that may be hidden inside an apparently simple point of light. A continuous spectrum contains a broad and relatively smooth range of wavelengths. Hot, dense matter often produces radiation resembling this form. An emission spectrum contains bright lines or bands at particular wavelengths, commonly produced by excited atoms, ions, or molecules in a thin gas. An absorption spectrum contains dark features where selected wavelengths have been removed from a broader background. During the early 19th century, the German instrument maker Joseph von Fraunhofer mapped hundreds of dark lines in the spectrum of sunlight. These Fraunhofer lines were measured long before their full meaning was understood. Later, the German physicist Gustav Kirchhoff and the German chemist Robert Bunsen showed that chemical elements emit and absorb characteristic wavelengths. Each element possesses a distinctive pattern linked to the allowed energy states of its electrons. The same pattern observed in a laboratory can appear in the light from a star. Astronomers can therefore identify hydrogen, helium, sodium, calcium, iron, and many other elements without ever touching the object being studied. Spectral lines also reveal temperature, density, pressure, ionization, and magnetic conditions. Their widths, strengths, and shapes contain information about motion and the environments where the radiation formed. Motion along the line of sight can shift the observed wavelengths through the Doppler effect. When a source moves towards an observer, its spectral features shift towards shorter wavelengths. This is called blue shift. When it moves away, the features shift towards longer wavelengths, producing redshift. Astronomers use these shifts to measure the radial motion of stars, gas clouds, and galaxies. The method can even reveal an unseen orbiting planet. As the planet and its star move around their shared centre of mass, the star wobbles slightly towards and away from Earth. Small periodic shifts in its spectrum can betray the planet's presence. Not every astronomical redshift is an ordinary Doppler shift caused by motion through space. Light travelling across an expanding universe can have its wavelength stretched as space itself expands. This is cosmological redshift. The greater the cosmic expansion during the light's journey, the more its wavelength is stretched. Observations of this effect helped establish that the universe is expanding, and later contributed to evidence that the expansion is accelerating. Gravity also changes the frequency of light. Albert Einstein's general theory of relativity describes gravity as the curvature of spacetime. Light travelling from a region of stronger gravity to one of weaker gravity is observed at a lower frequency and longer wavelength. This is gravitational redshift. The effect has been measured near Earth and observed in astronomical environments. It is especially important around compact objects such as white dwarfs, neutron stars, and black holes. Curved space-time also changes the path followed by light. A sufficiently massive object can act as a gravitational lens, bending radiation from a more distant source. In 1919, the British astronomer Arthur Eddington led one of the expeditions that observed stars near the Sun during a total solar eclipse. Their apparent positions were shifted in the direction predicted by general relativity. The expedition became famous as an early confirmation of Einstein's theory, although the measurements were difficult, and the historical story is more complicated than the simple tale of one perfect experiment settling everything at once. Modern gravitational lensing is observed with far greater precision. Galaxies and galaxy clusters can stretch background objects into arcs, create multiple images, or magnify sources that would otherwise be too faint to detect. The amount of distortion reveals the distribution of mass in the lens, including dark matter that emits no ordinary light. Weak lensing across large areas of sky allows astronomers to map invisible matter statistically and study the growth of cosmic structure. Visible light provides only one part of this information. Different regions of the electromagnetic spectrum reveal different processes, Radio telescopes detect cool gas, pulsars, synchrotron radiation, and enormous jets from active galaxies. The Atacama Large Millimeter/Submillimeter Array studies cold molecular clouds, dust, and the early stages of star and planet formation. Infrared observatories can see through dust and detect relatively cool objects. The James Webb Space Telescope operated through collaboration involving the National Aeronautics and Space Administration, the European Space Agency and the Canadian Space Agency, observes distant galaxies, forming stars and exoplanet atmospheres mainly in infrared wavelengths. The Hubble Space Telescope observes primarily visible and ultraviolet light, revealing stars, nebulae, galaxies, and deep views of the universe. The Chandra X-ray Observatory detects extremely energetic environments, including hot gas in galaxy clusters, supernova remnants, and matter heated near black holes. Gamma-ray instruments observe some of the most violent processes known, including gamma-ray bursts, radioactive decay, and powerful particle acceleration. Every wavelength range contributes a different layer. A galaxy that appears calm in visible light may contain intense radio jets or a brilliant X-ray source at its center. A dark cloud may block visible starlight while glowing in infrared radiation and emitting radio signals from molecules inside it. One of the oldest electromagnetic signals available is the cosmic microwave background. This radiation was released when the universe was roughly 380,000 years old, after it cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that time, free electrons repeatedly scattered photons, making the universe opaque. Once neutral atoms formed, much of the radiation could travel freely. Cosmic expansion later stretched it into microwave wavelengths. Measurements by observatories including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck spacecraft revealed tiny variations in this ancient radiation. Those patterns contain information about the universe's early density, composition, geometry, and later development. Polarization adds another source of evidence. The orientation of electromagnetic waves can reveal scattering processes, magnetic fields, and the structure of emitting regions. Polarized light helps astronomers study stellar atmospheres, interstellar dust, black hole environments, and conditions in the early universe. Through direct images, spectra, timing, redshift, polarization, and lensing, light reveals objects that may never be seen in the ordinary sense. Exoplanets can be inferred from starlight. Black holes can be identified through heated matter and gravitational effects. Dark matter can be mapped through the bending of background light. Expanding space leaves its signature in stretched wavelengths, while distant supernovae reveal the accelerating expansion of the cosmos. The observable universe is therefore a vast archive assembled from arriving photons. Each one carries traces of where it began, how long it travelled, and what happened along its path. Some bring news only minutes old. Others complete journeys lasting billions of years. Together they allow a small planet around an ordinary star to reconstruct much of cosmic history from light that has finally reached the end of its voyage. Light is understood more deeply than almost any other physical phenomenon, yet it still leads directly towards some of the largest unanswered questions in science. At everyday scales, classical electromagnetism describes light with remarkable accuracy. James Clerk Maxwell's equations explain how changing electric and magnetic fields propagate through space as electromagnetic waves. Geometric optics predicts how those waves reflect from mirrors and refract through lenses. Wave optics accounts for interference, diffraction, and polarization. Albert Einstein's special theory of relativity explains why light travels through vacuum at the same measured speed for every inertial observer. His general theory of relativity describes how light follows the geometry of curved spacetime near stars, galaxies, and black holes. At quantum scales, photons and electromagnetic interactions are described by quantum electrodynamics. This theory explains the emission, absorption, and scattering of light with extraordinary precision. These descriptions are not speculative alternatives competing for attention. They are firmly established theories supported by enormous bodies of evidence. Their predictions guide technologies ranging from cameras and lasers to satellite navigation and particle accelerators. The uncertainty begins when physicists try to place all of these successful ideas inside one complete framework. Quantum electrodynamics combines quantum mechanics, electromagnetism, and special relativity. It describes interactions between charged particles and the electromagnetic field. However, it does not include gravity as a fully quantum interaction. General relativity treats gravity as the curvature of spacetime. Light follows paths called null geodesics through that curved geometry. Near a massive body, its route can bend, its frequency can shift, and its travel time can change. This description works extremely well for planets, stars, galaxies, and black holes. Yet general relativity treats spacetime as a smooth classical structure, while quantum theory describes fields and interactions through probabilities, quantization, and uncertainty. Under ordinary conditions, the two frameworks can be used together without serious difficulty. Problems arise in extreme environments where strong gravity and quantum effects should both matter, such as the earliest moments of the universe or the deepest regions associated with black holes. A complete quantum theory of gravity remains unfinished. String theory is one candidate framework. It proposes that the fundamental ingredients of nature may be tiny extended strings rather than dimensionless point particles. Different patterns of vibration would appear as different particles, and one mode naturally possesses properties associated with a hypothetical quantum of gravity called the graviton. Loop quantum gravity follows a different route. It attempts to quantize space-time geometry itself, suggesting that quantities such as area and volume may have discrete quantum structures at extremely small scales. Neither string theory nor loop quantum gravity has received decisive experimental confirmation. They are serious research programs, not established descriptions on the same footing as quantum electrodynamics or general relativity. Light is also central to tests of quantum entanglement. Two photons can be prepared in a shared quantum state, so that measurements of properties such as polarization display correlations stronger than classical local models allow. Entangled photons may also use time-bin states, where the relevant alternatives involve different possible emission or arrival times. These states can be particularly useful when photons travel through optical fibers over long distances. The physicist John Bell showed mathematically that certain correlations predicted by quantum mechanics cannot be reproduced by a broad class of local hidden variable theories. Bell's theorem transformed a philosophical argument about quantum reality into an experimentally testable question. Experiments by John Clauser, Alain Aspect, and Anton Zeilinger progressively tested Bell inequalities using entangled photons and increasingly sophisticated arrangements. The observed violations agree with quantum predictions and rule out local hidden variable explanations of the tested kind. The conclusion is subtle. Nature cannot be described as though each photon simply carries a complete set of predetermined local instructions for every possible measurement. Entanglement does not, however, allow usable information to travel faster than light. Each local result remains individually unpredictable. The correlations become visible only when results from the separated measurements are later compared through ordinary communication. Relativistic causality therefore remains intact. These principles are being adapted for quantum technologies. Quantum cryptography can use individual photons and quantum measurement to reveal certain attempts at interception. Quantum communication aims to distribute quantum states or entanglement across networks. Quantum teleportation transfers an unknown quantum state from one system to another using shared entanglement and ordinary classical information. It does not transport matter, people, or energy instantaneously. The original state is destroyed in the process, and the required classical message cannot travel faster than light. Modern photonics research extends far beyond traditional lenses and mirrors. Integrated optical circuits guide photons through microscopic structures on chips. Single photon sources aim to release controlled individual quanta for communication, sensing, and computing. Frequency combs use lasers to produce precisely spaced spectral lines, rather like the markings on an extraordinarily accurate ruler for light. They support precision spectroscopy, measurements of time, and searches for subtle changes in physical laws. Metamaterials are engineered structures whose optical behavior depends on carefully arranged features, often smaller than the wavelength being manipulated. They can produce unusual refraction, focusing and control of electromagnetic waves, although popular claims about effortless invisibility usually travel somewhat farther than the laboratory results. Optical clocks measure time using extremely stable frequencies associated with electronic transitions in atoms or ions. The best systems are so sensitive that differences in gravitational potential over small changes in height can alter their ticking through gravitational time dilation. Laser light also allows physicists to detect disturbances that are not electromagnetic at all. The laser interferometer, gravitational wave observatory, uses long perpendicular arms and carefully controlled laser beams to measure passing gravitational waves. A gravitational wave slightly stretches one arm while compressing the other. The resulting difference in optical path length changes the interference pattern. The measured changes can be far smaller than the width of a proton. In 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of gravitational waves from merging black holes, using light to reveal ripples in spacetime itself. Other experiments search for even weaker signals. Some dark matter candidates might interact very faintly with photons, alter optical cavities, or convert into detectable electromagnetic radiation under special conditions. Precision spectroscopy and optical clocks can test whether quantities called fundamental constants remain unchanged across time and space. Laboratory instruments also search for hypothetical particles that could couple weakly to light. No such experiment has yet produced a definitive discovery that settles the nature of dark matter or reveals a confirmed variation in the fundamental constants. Questions also remain within quantum theory itself. Physicists continue to debate how measurement produces definite recorded outcomes, how best to describe photon localization, and exactly where a classical electromagnetic field becomes the more useful description of a many-photon quantum state. These debates do not mean that nothing is known. Quantum theory predicts experimental results with exceptional success. The open questions concern the deeper interpretation, limits, and unification of that framework. Light actually works through several connected layers. Electromagnetic fields determine its classical propagation. Relativity describes its invariant speed and its motion through curved spacetime. Quantum theory governs its creation, absorption, and detection as photons. The remaining mysteries begin where those successful layers meet. Light has already revealed the atomic structure of matter, the expansion of the universe, the existence of quantum entanglement, and the curvature of spacetime. It may yet expose dark matter, quantum gravity, or entirely unfamiliar physics. Its unanswered questions do not weaken what has already been established. They mark the edge of an exceptionally successful understanding, where one of nature's oldest messengers continues to illuminate the limits of human knowledge. Light actually works not through one simple mechanism, but through several connected layers of physics. Electromagnetism describes its changing electric and magnetic fields. Relativity explains its invariant speed and its path through space-time. Quantum physics governs its emission, absorption, and detection, while matter determines how it is reflected, refracted, scattered or transmitted. The journey began with ancient ray models and the careful optics of Ibn al-Haytham, then moved through James Clerk Maxwell's electromagnetic waves, Albert Einstein's relativity, and the modern description of photons as quantized excitations of the electromagnetic field. Along the way, light revealed its full range of behaviours. It can be emitted by hot matter or changing quantum states, propagate through vacuum, reflect from surfaces, refract through materials, scatter through atmospheres, diffract around openings, interfere with itself, carry polarization, transfer energy through absorption, and finally become a signal inside a detector or living eye. Visible light is only a narrow biological window within an electromagnetic spectrum stretching from radio waves to gamma rays. Even the colours within that window do not belong entirely to wavelengths, objects, or the brain. They emerge from illumination, material interactions, retinal responses, and neural interpretation working together. Wave and photon descriptions are therefore not rival stories. They are related views of the same electromagnetic field, useful at different scales and under different experimental conditions. Light connects vision with chemistry, electronics, communication, astronomy, relativity, and quantum theory. A single arriving photon may carry evidence of a star's temperature, a distant atmosphere's composition, a galaxy's motion, or the curvature of space-time. Every illuminated room, visible surface, and distant point of starlight is part of an ongoing exchange between electromagnetic fields, matter, and the observer. Light remains an ordinary companion and one of nature's deepest messengers, carrying information across rooms, across worlds, and through almost the entire observable history of the universe.